Night slides over the quiet deserts of Earth, and a thin seam of stars opens like a wound of light. In that hush, NASA's telescopes keep their own kind of vigil. They do not stare for beauty, they count. They listen to gravity. They measure the fainting of starlight when a planet crosses a distant face of fire. Every dip becomes a syllable, every repeat a word, until a hidden alphabet spells the shape of a world. Out of that patient language came a revelation that felt almost impolite, as if the universe had been keeping a family secret. There are planets that sit between Earth and Neptune in size, heavy enough to carry their own weather, light enough to hold it close, and they appear everywhere. They crowd the star fields like seeds on a wind. And yet this planet shape is missing from the solar system that taught humanity the very word planet. It is a hole in the home map, an outline that should be here but is not. Imagine a world larger than Earth but smaller than Neptune. Imagine skies that may be pale green with photochemical haze, or ink dark above clouds the colour of steel. The gravity is a little heavier than home. The air might be hydrogen light and buoyant. It might be steam thick enough to smother mountains. It might be something no human chemistry kit has ever breathed. Picture a sea that never grows quiet because the air itself presses like a second ocean, or a crust that trembles atop a mantle of high-pressure ices that do not melt so much as transform, water turning to strange crystal flavours under the iron thumb of depth. Now picture this not once, not twice, but by the thousands. The sky is full of such possibilities. These worlds took shape first as numbers, as carefully subtracted brightness, as error bars that refused to shrink. The Kepler spacecraft stared at a single patch of constellation like a monk living in a single room, and from the monotony pulled a census nobody expected. Transits arrived with clockwork regularity. Periods could be counted. Sizes inferred. Orbits sketched like chalk rings on a blackboard. Spitzer confirmed the rhythm in infrared. Tess broadened the search across nearly the whole sky, and Hubble followed with stare-downs that tried to read atmospheres out of rainbow fingerprints. The most astonishing part was not a spectacle of rarity. It was repetition. World after world wore the same rough silhouette, as if nature had a favourite mould. The galaxy seemed to bake these planets again and again. The riddle begins in the silence of our own yard. The solar system offers Mercury, a stone scorched to a dull shine. Venus, a furnace wrapped in cloud. Earth, balanced and blue. Mars, a rusty whisper of an ocean that has forgotten its name. Then the view jumps, with no half-step, to the methane blues of Neptune and the swollen bouquet of Jupiter's storms. Between Earth and Neptune, there is nothing. No super-Earth to test a bridge of habitability. No sub-Neptune to hint at how gas shrouds rise and fall. The absence feels wrong in a way that numbers alone cannot express. It is like gliding a fingertip across a piano and finding a missing key where a note should be. The melody goes on, but the song is changed. What would such a planet be, really, once reduced to a face in a telescope and a calculus of gravity? Mass tells part of the truth. Radius tells another. Together they whisper density, the ghost of composition. A denser figure leans toward rock and metal. A lighter figure suggests gases or waters laid thick. But the galaxy refuses an easy label. There are worlds in this size class with densities fit for iron fist interiors, and others with figures so delicate that only helium lightness seems plausible. There are climates that probably boil and also climates that could run cold as shadow. NASA's instruments record the spectrum of starlight that slips through their skies during transits, hoping for the sawtooth cuts of water vapor, methane, carbon dioxide, or other familiar signatures. The signal often arrives smothered by haze or flattened by clouds that behave like curtains drawn across a window. What emerges feels less like a portrait and more like a silhouette. Yet silhouettes can be powerful. They concentrate imagination. Somewhere out there, a planet just a bit larger than home could wear a thin hydrogen veil over a global sea, a place where storms march like armies and lightning burns in turquoise arcs. Somewhere else, a similar body could carry a mantle of ice phases that do not exist on Earth, trapped under a sky that barely moves, its winds choked by weight. Another cousin might present land and water in fragments, continents crusted with salts, oceans that are not quite water as water is understood, perhaps coloured by dissolved minerals that give the waves a bruised hue. The human mind bends toward metaphor when data will not easily speak. Worlds become mirrors. They reflect wishes and fears, the dream of a second Earth, the dread of a silent nothing. But the mystery finds its dignity in restraint. It insists on being itself. NASA's machines answer with more listening. Photometers sip light. Gyroscopes hold a star's face steady. Reaction wheels hum with a tiny hymn to precision. Observing time is a currency spent carefully. Targets are chosen, not only for the chance of striking a clear spectrum, but for the story their orbits hint at. A cluster of planets kneeling close to a faint star suggests a history written in migration, as if the system drifted inward during its childhood. A solitary planet near a bright sun suggests a harsher upbringing, perhaps a life lived in flares and winds that gutted the sky. The craft relay their harvest to antennae on Earth, and the numbers slip into laboratories where models coil around them like vines around a trellis. For each candidate, 1,000 versions bloom, each one a possible world. The effect on the imagination is double-edged. Abundance is solace. The night does not feel empty, but abundance deepens the thirst for specificity. To know that the most common planets discovered by NASA do not exist in the place humans call home is to feel a low, persistent ache. Perhaps the solar system is a minority report in a universe of other scripts. Perhaps there were once members of this size class here, and time or dynamics erased them. Perhaps there is a rule that forbids their birth in our particular arrangement of disk and star. Facts are careful creatures. They arrive slowly, and they often come dressed in ambiguity. Yet the emotional consequence blossoms immediately. Humanity is confronted with a category that challenges its provincial definitions. Planet is no longer a simple ladder that ends in Neptune. It is a wide field where new paths fork everywhere. Under the quiet authority of these discoveries, the question forms with the simplicity of a bell. What are these worlds? Not in allegory, not as metaphors, but in their own right. What rocks hold their cores together? What gases write their weather? What heat rises from their insides? And what light sculpts their skies? If some of them carry seas, what depths do those waters reach? And what salts give them their flavours? If some carry thick hydrogen cloaks, what chemistry stirs in that light air? And what ancient processes decide how long such a cloak endures? The puzzle does not feel academic. It reaches into the oldest human habits, the way sailors once traced shorelines from a horizon and named capes they had not yet walked. A map grows bigger than the ship that carries it. Night remains, and on a desert ridge, a dome slowly turns to face a star that most eyes would ignore. Instruments take their measure again. The planet will cross its sun in a little while, and the light will dim by less than 1%, and that small grief in brightness will point to a body bigger than Earth, smaller than Neptune, a population that has become a chorus. The naming will wait, the certainty will wait. For now there is the sublime fact that the universe builds many doors that Earth never learned to open. The instruments keep their vigil, and the sky keeps its counsel, and a new silhouette of worldliness thickens in the dark like weather. It is elegant to be humbled by something so common. It is elegant to hold a question long enough that it begins to glow. The planet crosses, the light returns, the signal is logged, and a mystery takes one more breath in the thin air between knowing and wonder. The story of these intermediate worlds began with a group of engineers and astronomers who decided that patience could be an instrument. In clean rooms and control centers, they shaped a spacecraft into a clock that would count the tiniest flickers in starlight. William Barucki, a quiet advocate with a long memory for good ideas, gathered the case and carried it through years of proposals and revisions until the plan was undeniable. The spacecraft took a simple name that sounded like a surname from an old observatory. It launched into the dark with a single purpose. It would stare at one patch of sky and hold its breath for years. The chosen field lay between the constellations of Cygnus and Lyra, a rich quilt of stars far from the sun's glare. The spacecraft faced that window and refused to look away. Sunlight pressed on its solar arrays. Reaction wheels kept its gaze steady. A vast camera of many detectors turned photons into counts, and counts into curves, and curves into the shallow dimmings that mark a transit. If a planet passed in front of its star, the star's brightness would dip by a fraction and then recover. The spacecraft would notice. It would mark the time. A second dip would draw a circle around a possibility. A third would earn a deeper look. From that rhythm, orbits could be plotted and sizes inferred. Teams at NASA Ames and partner institutions learned to listen to the noise with almost musical skill. Cosmic rays spiked the detectors. Spacecraft temperature drifted. Stars themselves flickered with spots and flares. The analysts built pipelines that could tell a whisper from a cough. The data poured in for years. The first confirmed planets were hot and close, skimming their suns in days. The small transits easy to find by abundance rather than by ease. Then the catalogue began to change character. Planets appeared whose radii sat just above Earth's and below Neptune's. They came again and again until the list seemed to prefer them. The spacecraft had not been sent to find a favourite. It found one anyway. Kepler 10b arrived like a stone in a still pond. It was small, it was scorched, and it showed that the instrument could measure a world only slightly larger than Earth. Kepler 22b followed with a softer light. It carried a size that suggested a deeper envelope, a cresting of atmosphere beyond stone and iron. The Kepler 11 system opened like a nested set of boxes. Several planets, all close to their star, all in the intermediate regime, crossed in an elegant dance. Each confirmation required a network of hands. Archival images checked for background stars. Adaptive optics resolved false companions. Radial velocity instruments on large telescopes weighed the candidates where possible by watching the parent stars tug back and forth under the influence of orbiting masses. The mass measurements arrived with their own confidences and doubts, adding depth to the silhouettes sketched by transits. The spacecraft's health faltered when critical wheels failed. Rather than end the effort, the team turned the limitation into a new design. With the sun as a stabilizing force, the mission looked along the ecliptic in successive campaigns. The targets changed. The method did not. Fresh sequences of dimmings continued to trace the outlines of worlds, including many in the same perplexing size range. The younger sibling of this effort took shape on the ground in the form of an all-sky surveyor with 4 wide cameras. It launched from Florida into a resonant orbit that keeps it close enough for quick communication and far enough for long, quiet exposures. Where the first mission had stared at a single window, this new survey tiled almost the entire sky in month-long sectors, returning later to revisit and refine. Nearby, brighter stars filled the new lists. Planets around them became easier targets for weighing and for atmospheric attempts. The count of intermediate-sized worlds swelled further, and now they resided around stars whose names could be spoken with less catalogue formality. The logic of discovery demanded partnership. A retired infrared telescope that had once pursued dust and expanding space turned its mirror to transits and provided confirmations when visible light could not. Large ground-based spectrographs added their slow metronome of stellar wobbles. When the time came to try to taste the air of these planets, the veteran space telescope trained its mirrors on the moment of transit and watched for colours of light absorbed by gases in the limb of a world. Scientists kept careful books. Each candidate received a number. Each confirmation received a knighthood of letters. The catalogues learned to track false positives that came from eclipsing pairs of stars blended into a single point on the detector, and from other illusions of geometry. Statistical validation became an art. If a star showed multiple transiting companions, the odds shifted strongly toward true planets. If the dips arrived with different shapes, different durations, different depths consistent with their periods, the case grew. When possible, the Doppler signal of the host star, sealed the verdict with a measure of mass. Not every world could be weighed in this way. The faintest hosts and the smallest planets remained elusive to the heaviest spectrographs. Yet the population emerged with clarity. Nature liked to build bodies between Earth and Neptune. A few worlds turned into characters that could carry a narrative of technique. One such planet lived around a small, cool star and transited on a comfortable clock. The survey that found it belonged to the second spacecraft and its follow-ups. Observers added intricate timing to its transit sequence and measured a hint of other bodies nearby through the slight irregularities that arose when gravity made them tug on each other. Another example came from the original field and displayed two planets with alarmingly different densities despite their adjacent orbits, as if they had been forged under separate rules and captured by chance. The catalogue contained other surprises. Some of these intermediate worlds clung close to their stars and lived in high radiation. Others sat farther out, where light thinned and the pace of orbit slowed. The range of locations compressed any single story of origin into something too tight to hold. Crucial to this unfolding was the active follow-up carried out by coordinated teams. Transit surveys find sizes, spectrographs find masses when the stars are calm enough and bright enough. Together, the pair provide densities, high-cadence photometry from the ground checks for subtle secondary eclipses that would betray a star hiding rather than a planet crossing. High-resolution imaging rules out near neighbours. Even the absence of a detectable wobble sometimes tells a truth by setting an upper limit on mass that implies a puffy envelope. Each technique added a layer, and each layer sharpened the outline of the population. The when and the where of this discovery trace a map of observatories rather than a single mountaintop. The original launch left Earth in 2009, and the first harvest came a few years later. The second survey arose in 2018 and began carving the sky into sectors that built a bright star catalogue for transit work. Infrared confirmations continued until a graceful retirement of a venerable eye in 2020. Large optical telescopes in Hawaii and Chile supplied the counterpoint of stellar motion. The old space observatory with mirrors of gold studied atmospheres of a few emblematic worlds after its own arrival at a deep space waypoint. Behind all of it stood an army of analysts, graduate students learning to trust and distrust patterns, senior scientists who remembered the first debates about whether small dips could be believed, and engineers who kept the spacecraft on task through the gentle violence of space. The how of it is a triumph of subtlety. Photons leave a star and fan outward. A planet robs a few when it passes. The reduction looks like a sigh. If the planet carries an atmosphere, the starlight that grazes it will be tinted by molecules and aerosols. If other planets orbit nearby, their mutual pulls will make the timing of transits deviate from perfect periodicity by seconds or minutes. If the host star vibrates or spots over time, those changes create complications that must be teased apart from planetary signals. The craft that do this work are not dramatic by the standards of rockets and rovers. Their drama lies in their stillness, in the insistence that looking quietly for a long time will reveal something loud. What emerged from this program of patience was not a parade of rare beasts, but a herd. The intermediate-sized planets seemed to prefer orbits of days to weeks around small stars, and longer spans around larger ones, a simple reflection of detectability mixed with genuine architecture. Their transit depths often landed in a range that a well-tuned instrument could catch. That detectability does not cheapen the finding. It only explains why the reservoir was tapped so quickly. The deeper truth is that planet formation appears to make these bodies readily. The discovery phase established the fact of abundance and put faces on a few members of the family. The names became familiar to the workers who logged them. The public learned a handful. The catalogues did not mind the anonymity of the rest. They lived in tables and charts, and in the gentle curves of light that first betrayed their existence. The first shock arrived in a graph. Radii of hundreds of worlds were set along one axis, the number of planets along the other, a simple census that should have drawn a smooth hill if nature favoured continuity. Instead, the hill was split. A hollow ran through the distribution near twice Earth's radius. like a riverbed cut through sand. On one side, clustered planets hardly larger than Earth, dense enough to hint at rock and metal. On the other side rose a second crowd, bloated enough to suggest envelopes of light gas. Between them lay a valley where few worlds lived. The eye did not need statistics to feel the break. The pattern announced itself with an economy that felt ruthless. The intuition of many investigators had leaned toward a gradual spectrum of sizes and compositions. If protoplanetary disks built small rocky bodies that grew by swallowing pebbles and planetesimals, and if they also built larger ice and gas giants by crossing thresholds of accretion, then a steady blend of in-betweens seemed reasonable. The census refused this comfort. Something was carving a gulf between compact super-Earths and puffy sub-Neptunes. The finding did not simply add a footnote to formation theory. It demanded a new paragraph. Planetary physics speaks a language of thresholds. A core that gathers a little hydrogen and helium may remain a stone wrapped in air. A core that gathers a little more can suffer a runaway, where gas piles on faster than it can be shed. Gravity, temperature, and time negotiate a fragile peace. The valley in radius hinted that a tipping point was common. Either a young planet held its envelope and grew into the larger class, or it shed that envelope and shrank into the smaller class. The middle realm existed, but as a transient. Nature seemed to hurry her children across it. This would have been startling in any context. It became more so when placed beside another emptiness. The family of planets around the Sun has no member in the radius range most easily populated elsewhere. Mercury is small and bare. Venus and Earth are slightly larger, but stand firmly on the rocky side. Mars sits below them like a quiet cousin. Then the neighborhood leaps to Neptune, a world large enough to cradle a deep atmosphere and exotic interiors. The solar system owns a private valley that runs even wider than the statistical one. The human textbook on planets had been written in a house that lacked the most common furniture in the galaxy. Explanations gathered, some with the confidence of mathematics, others with the humility of working hypotheses. One family of ideas looked upward to the star. Young suns pour ultraviolet and X-ray photons into their neighborhoods, and their winds carry energy and momentum. Planets that sit close can have their atmospheres heated at the top, producing particles energetic enough to escape. Over millions of years, this external stripping can turn a small sub-Neptune into a bare core that masquerades as a super-Earth. The process would be more effective for lighter envelopes and for smaller planets, naturally creating a divide. Another family of ideas looked inward to the heat already sealed within young planets. As a newborn world cools, its interior releases energy that must find a path outward. If a thin envelope sits on top, this inner heat can loft it, expand it, and make escape easier even without much help from the star. The planet becomes a slow lantern expelling its own air. Over time, the envelope thins, and the radius contracts until the world rests on the rocky side. If an envelope is thick, gravity can keep its hold, and the planet remains a sub-Neptune. The internal thermostat, not the stellar furnace, sets the border. Both camps can draw curves that intersect the data. That is the strength and the source of disquiet. It suggests that reality may use both tools at different epochs, or with different intensities depending on mass, orbit, and stellar temperament. The radius valley then becomes a composite signature of several processes walking in step toward a similar outcome. When early analyses showed that the valley moved slightly with the brightness of the star and with the orbital period of the planet, the plot deepened. A valley that shifts with stellar activity leans toward external stripping. A valley that shifts with planet mass leans toward internal cooling. In some systems, both trends appear. It is a riddle that does not apologize for its nuance. Other puzzles appeared as satellites of the main surprise. There is a desert where hot Neptunes should be plentiful. Very close to stars, nature seems to prefer giants or small rocky planets, while mid-sized atmospheres go missing, perhaps ablated by heat or never assembled at all. There are also pairs of neighboring planets that do not match, one dense and small, the other inflated and light, circling the same star at similar distances. These mismatches violate the tidy expectation that siblings share traits. They whisper of formation histories that diverged early, or of later events that pruned one and spared the other. Surface, gravity, and atmospheric chemistry complicate the picture. A planet only slightly larger than Earth can carry an envelope that swells its radius dramatically while contributing only a small fraction of the total mass. Another planet of similar radius can be nearly all rock, wearing only a thin cap of air. Mass by itself cannot tell the whole story. Radius by itself cannot either. Density helps, but it blends together iron, silicates, water phases, and gases into a single statistic. The valley divides populations that are already difficult to label. Theories of disk evolution feel the tremor from this finding. If pebbles drift inward through a young disk and feed cores efficiently near the star, then many seeds should reach the mass needed to snag gas before the disk dissipates. Yet the valley tells of envelopes lost or never deeply gained. Perhaps magnetic fields in the disk steer gas away from the smallest cores. Perhaps the timing of disk clearing decides fates with a precision measured in hundreds of thousands of years. Perhaps collisions after formation chip away atmospheres, or even grind down planets to their skeletal cores, revising radii into the rocky regime. Each scenario can reproduce a facet of the catalogue. None, on its own, captures the full mirror. The emotional weight of the result rests in its clarity. Astronomy often trades in trends that melt when scrutinized, but this valley has stayed. As more planets are counted, the gap persists. As methods improve, the outline remains. It is a negative space that forces the mind to draw new shapes around it. The instruments do not know romance, yet the effect on the human eye is strangely aesthetic. A population pours downhill into two basins, leaving a dry channel between. Order emerges from the chaos of star fields and light curves. It is beautiful and inconvenient at once. Even the language around these planets feels unfinished. Terms like super-Earth or sub-Neptune are inherited labels that imply known relationships to two familiar worlds. The valley suggests that nature does not think in that vocabulary. These are not apprentices to Earth or failed cousins of Neptune. They are their own class with its own physics of origin and survival. Their skies may be thin or thick. Their interiors may be oceans of high-pressure water or mantles of silicate and iron. The gap in radii tells us that the universe pushes them toward two stable solutions, but it does not say what kinds of lives they lead within those solutions. Seen from the vantage of method, the surprise instructs humility. Diagrams that once tried to fold all worlds into a single curve of size versus period now yield to maps with islands and channels. The valley cautions against assuming that one process dominates. It recommends careful attention to stellar ages, to activity cycles, to the metallicity of disks, to the choreography of migration, and to the intimate arithmetic of energy budgets within small planets. In that arithmetic, where photons, heat, and molecules escape, where gravity binds and time unbinds, the radius valley reads like a ledger written in light. What shocked observers first now serves as a compass. A planet measured near the valley invites a deeper look. A system that piles several worlds on one side or the other becomes a laboratory for testing which winds blow strongest in that neighborhood. The empty space between the peaks of the distribution is not a void in knowledge. It is a signpost. The sky allowed humanity to find a rule by finding a break. Few moments in science are more bracing than that. The census deepened when weights joined sizes. Precision spectrographs began to hear the tiny back and forth of stars as unseen companions tugged on them. Transit timing variations turned into a second language, where small departures from a perfect schedule betrayed the gravity of neighboring planets. With those two measures, mass and radius could link arms to speak density, and density could whisper about interiors. A cloud of points appeared on the mass-radius plane, each a world resolved not only as a silhouette, but as a body with heft. The pattern that emerged refused a single recipe. Some planets near twice Earth's radius were as compact as forged iron. Others with similar size floated on densities that implied thick envelopes of light gas. The data did not collapse toward an average life story. It spread outward like branches. Interior models tried to keep pace. A given mass and radius can be made by many mixtures, so the models learned to live with families of answers. A rocky core of silicate and iron wrapped in a few percent by mass of hydrogen and helium can swell to the same radius as a world built mostly of water in high-pressure phases with only a thin sky. Priors from stellar composition helped, since planets inherit the metallic taste of their parent stars. Even so, the results arrived with ambiguity that was not failure but truth. Nature had built variety into a size range that many had expected to be pedestrian. Modest differences in envelope fraction made large differences in radius. Modest differences in ice content changed the weight a planet could carry without showing it in silhouette. The lesson was simple and stern. Two planets of the same radius could lead opposite lives. Stellar influence sharpened the picture. When densities were plotted against the heat a planet receives from its star, trends took on relief. Close-in planets leaned denser, as if their skies had been shaved down by time. Farther out, planets showed more puff, consistent with envelopes that had endured. Age estimates added another axis. Around older stars, the small planets looked even more like stripped cores, while some mid-sized bodies still clung to their veils. The combination of irradiation and age began to map an arc of evolution, young and puffy to old and compact for many members of the class, with exceptions that kept humility intact. The sky itself offered testimony during and between transits. When starlight slipped through a planetary limb, subtle color changes told of molecules, aerosols, and clouds. The results arrived in two dialects. Some targets yielded spectra with the gentle teeth of water vapor and hints of other gases, evidence that the curtains were thin enough to see through. Others returned stubbornly flat lines, a sign that hazes or clouds muted the chemical signatures. The flatness did not mean emptiness. It meant weather. Photochemical mists can rise from hydrogen-rich mixtures under strong light, turning a planetary rim into frosted glass. High-altitude condensates of exotic salts or sulfides can do the same under cooler suns. The diversity of sky texture became a finding in its own right. Measurements outside of transits extended the view from chemistry to climate. Phase curves traced how brightness changed as planets pirouetted through their orbits, revealing day-night contrasts and heat transport. Some worlds shifted heat efficiently, their nights warmer than expected and their days a little softer, as if winds had found clean lanes. Others hoarded heat under the substellar point, hinting at sluggish circulation or deep radiative layers that trap energy. Occasional secondary eclipses at infrared wavelengths pinned down dayside temperatures directly. The numbers were often hotter than naive equilibrium would predict, a reminder that many of these worlds sit under unrelenting lamps and likely carry internal heat, still bleeding from formation. Escape left fingerprints that were elegant and stark. Spectra around helium's near-infrared line sometimes flared during transit, the signature of an extended exosphere drifting away like a comet tail. In a few cases, the signal arrived shifted, a wind in motion rather than a static halo. The detections confirmed that envelopes can be peeled and that the peel can be watched. They also granted leverage on escape rates when combined with models of stellar activity. The lightest atmospheres show this drama most vividly, but heavier skies can bleed too if heated strongly enough at the top. Each such measurement turned an abstract mechanism into an observed weather report for a world that no instrument could ever touch. Orbital architectures revealed habits of formation and adjustment. Period ratios between neighbors clustered just wide of simple resonances, as if migration had once shepherded them into near commensurabilities and later processes had nudged them apart. The near misses were not random. They painted a history of disks that moved planets gently and of later tides and perturbations that loosened the resonant grip. Eccentricities stayed small for many members of compact systems, which fit a past of smooth disk-driven migration rather than violent scattering. Yet solitary planets sometimes wore higher eccentricities, as if they had survived rougher company or exchanged angular momentum with unseen companions. The same size class thus appeared in both quiet quires and in lonelier orbits, expanding the range of plausible origin stories. Obliquity measurements, where available, added nuance. For a few bright hosts, the angle between stellar rotation and planetary orbit could be inferred from the subtle distortion of spectral lines during transit. Many small planets tracked well-aligned paths, consistent with birth in disks that maintained order. A minority did not. Tilted systems announced that even modest worlds can be torqued by companions or by processes that warp disks in youth. The intermediate population, therefore, does not belong solely to one school of dynamics. It lives across a spectrum of calm and mischief. Compositional clues arrived from star to planet comparisons. Metal-rich stars tended to host more planets in this regime, and those planets leaned a little heavier, a sign that disks with more solids feed core growth efficiently. The trend did not become a straight line. Stars of similar metallicity still produced wildly different families, yet the correlation urged formation models to include the chemistry of nurseries as an active agent, not a backdrop. Dust content and the sizes of drifting pebbles likely set the speed limits for cores and the thresholds for capturing gas before a disk thins. The data suggested that timing is everything. A planet born early in a gas-rich disk can drink more deeply. A planet born late arrives to a table already being cleared. Albedo entered the file as a quiet but potent parameter. Reflected light measurements for a handful of worlds showed surfaces or clouds that turned away more starlight than expected, while others drank light greedily and glowed with absorbed heat. Brightness in the optical hinted at high cloud decks or reflective hazes. Darkness hinted at deeper, clearer atmospheres loaded with absorbers. Together with thermal observations, these reflections help to balance energy budgets and to test circulation models that move heat from day to night. The patterns were messy in the human sense and rich in the scientific one. A category that looks uniform in a histogram carries multitudes when met at the level of weather. Geology made a distant entrance through inferences rather than direct sight. Ultra-short period, members of the class likely wear lava, oceans, or rock vapor atmospheres as surface minerals sublimate under raw light. Slightly cooler cousins may host magma reservoirs overlain by high-pressure steam. Farther out, internal pressures can press water into unfamiliar ices that behave more like minerals than like anything poured from a kettle. Tidal forces in multi-planet systems may knead interiors and feed volcanism or cryovolcanism. None of this has been photographed. All of it flows naturally from physics tested in other contexts. The mass-radius pairs demand interiors that are not simple repeats of terrestrial templates. Multiplicity statistics stitched a final theme. Systems with several intermediate worlds often showed gentle spacing, low mutual inclinations, and regular transit chains that allowed timing analyses to weigh them en masse. Singletons around bright stars, by contrast, loomed as better targets for atmospheric work. The two groups served different kinds of understanding. The first revealed structure and dynamics. The second revealed chemistry and climate. Together, they made the class feel less like a curiosity and more like a common architecture of planetary neighborhoods. The most important revelation hid in plain sight. More information did not erase the mystery. It sculpted it, adding mass to radius transformed outlines into bodies, adding spectra transformed bodies into climates, adding architecture transformed climates into family histories. At every upgrade, the category fractured into subtypes: thin veils and thick veils, vigorous winds and stagnant shells, compact chains of siblings and solitary drifters, hot skins of rock vapor, and cold mantles of exotic ice. The pattern refused to flatten into a single description because these worlds are governed by balances that are exquisitely sensitive to starting conditions. A percent more envelope, a million years earlier access to gas, a slightly redder or bluer star, and the fate of a planet diverges. The deeper data, therefore, offered a paradox that is not despair but invitation. The class is common, yet each instance is precise. The statistics are strong, yet the individuals are particular. The trends are persuasive, yet the exceptions are eloquent. With every new measurement, the shape of the unknown took on finer grain, like a coastline seen first from space, then from an aircraft, then from a cliff where the wind smells of salt. The numbers did not simply accumulate. They began to breathe. Complexity arrived like weather over warm water. At first, the sky looked simple. Then layers appeared, moving at different speeds, forming patterns that broke apart as soon as they were named. The intermediate planets refused to settle into a single script because every measurement opened two doors rather than one. Spectra flattened where theory promised sharp teeth of molecules. Densities that should have pointed to rock or gas pointed instead to both at once. Light curves that mapped clean orbits developed small tremors that hinted at unseen neighbors. Each rise in precision raised the number of plausible lives a planet could be living. Clouds were the most visible culprits and the least understood. A world with a hydrogen veil can build a haze from the top down when starlight cracks molecules and lets them recombine into sooty chains. A different world, warmer or heavier by only a small margin, can loft condensates from the bottom up, salts and sulfides mixing into bright decks that turn spectra into blank, pale sheets. The same radius and mass can wear either mask. Retrieval codes that try to pull composition out of starlight must decide whether a flat line means true absence or simply a curtain. The decision swings assumed chemistry by orders of magnitude. An atmosphere thought to be thick with water can become an atmosphere thought to be thin and dusty if the wrong veil is assumed. The planet does not change. The interpretation does. Stars complicate the picture in a quieter but equally stubborn way. A stellar surface is not a uniform lantern. It is mottled by spots and faculae, by magnetic knots and bright patches that drift in and out of view as the star rotates. When a planet transits, it samples a slice of the stellar face that may not match the average. The spectrum that looks like a planetary fingerprint can be stained by this local starlight. Tiny differences in color tilt in the data become traps for confident conclusions. The planet seems to reject water or methane or both until the stellar skin is modeled and the rejection softens. Precision pushes astronomy toward the details of its backlight. Without that correction, the mystery grows by accident. There is also the matter of ages. A young planet bloats with leftover heat. An old planet shrinks into its gravity well. Yet the clocks that date stars are not always steady. Rotation can spin down at different rates depending on magnetic history. Activity can masquerade as youth. Chemical clocks in stellar photospheres are informative yet not universal. When a world appears too puffy for its supposed age, two very different stories conflict. Either an unexpected source of interior heat sustains the envelope against contraction, or the stellar birthday was misread. Each possibility bears different consequences for how the class evolves. The data do not concede which correction to apply without a long negotiation. Mass measurements agree to disagree in certain systems. Transit timing variations can weigh planets by letting them tug on each other's schedules. Radial velocities can weigh them by watching the star's heartbeat of motion. In crowded neighborhoods, the two methods sing together. In sparse fields, they sometimes do not. Additional, non-transiting companions can warp the timing signal and hide in the radial velocity residuals. Stellar jitter can play false notes that sound like planetary pulls. A world can come out heavy in one ledger and light in the other. The statistics eventually reconcile as more data accrue, but during the reconciliation, the catalogue holds both numbers with a frown. The uncertainty leaks into density, then into interior models, then into habitability conjectures, like dye spreading through water. Energy budgets refuse to balance cleanly. Some planets reflect more visible light than their clouds would suggest. Others drink nearly every photon and still glow hotter than equilibrium by a margin too large to ignore. Circulation models that should move heat from dayside to nightside stall without warning in certain regimes and outperform expectation in others. A small change in metallicity, a small tweak to drag, and jet streams either slice the night side free from freezing or abandon it to black cold. Observers catch hints of eastward hotspots on one world and a stubborn substellar furnace on another, with almost identical irradiation. The rule that explains both keeps slipping through the fingers. Interiors resist a single recipe like a kitchen that keeps changing its oven. A few percent by mass of hydrogen and helium can swell a world past recognition. A mantle of high-pressure water phases can do something similar without any light gases at all. Iron fractions depend on where in a disk a core assembled and on how aggressively later impacts sculpted it. Even the word water misleads, because at hundreds of thousands of atmospheres, it ceases to be familiar and begins to behave like a conductor or a crystal pressed beyond intuition. Without a way to see through, the same bulk properties sketch multiple interiors with equal confidence. Each interior leads to a different surface pressure, to different chemistry, to different paths for heat to escape. The planet hides several biographies in a single pair of numbers. Formation histories fold the mystery further. Migration through a young disk can place a planet in a hot orbit gently, leaving resonant siblings nearby and a quiet, low eccentric path. Scattering can hurl a planet inward violently, break resonances, and tilt orbits relative to the stellar spin. Both stories have been read in the same size class. A world that looks carved by atmospheric loss could instead have been born lean, beyond the snow line, and then carried inward with only a skim of hydrogen to begin with. Another that looks born bloated could have formed in place but been fed by a slow drift of pebbles that delivered ices and volatiles quietly over millions of years. The fossils of those epochs live in patterns that observations only partially resolve. A single system can be read two ways until a new clue breaks the tie. Chemistry both promises and denies closure. Ratios of carbon to oxygen, of nitrogen to oxygen, should tag where in a disk a planet gathered its air, whether inside the water ice line or beyond it. In practice, the clouds and the light of the parent star warp those ratios until the uncertainties swallow the signal. The few atmospheres with clear molecular features display compositions that seem both plausible and disruptive. One shows more heavy elements than anticipated for its mass. Another shows less. A third refuses all offered templates and stands silent. The limited sample encourages caution, but even with caution the spread is larger than predictions that tried to be universal. Selection effects linger like a seam in fabric that keeps catching the hand. Transits favour systems that line up with the observer. Bright host stars are treasured for atmospheric work, which skews the sample towards certain neighbourhoods in the galaxy. Small stars dominate the accessible set for the smallest planets. Environments around such stars may be harsher, with flares and winds that thin skies differently than around larger suns. The catalogue is a teacher that grades with a bias. Correcting for geometry and brightness and stellar type requires models that themselves inherit assumptions from earlier eras. Progress is real. Confidence is cautious. Even where escape is seen directly, with helium lines flaring as a planet exhales into space, the rates are a riddle. The exospheres that drift like veils in transit represent a snapshot. They do not specify whether the planet will be stripped bare in 100 million years or keep a remnant for billions. When a mature world still wears a surprisingly thick envelope, a suspicion of hidden heating rises again. Tidal friction in a slightly eccentric orbit, ohmic dissipation in a partially ionized wind, latent heat released as phase changes churn the deep interior. Each mechanism has physics on its side. Each is difficult to confirm at arm's length. Magnetism adds one more layer of uncertainty. A magnetic field can shelter an atmosphere from the worst of a stellar wind, redirecting charged particles and softening the bite. It can also couple the wind to the upper atmosphere and inject energy that stirs escape. The field itself depends on rotation, on conductivity in the interior, on the existence of metallic hydrogen or salty high-pressure oceans. None of these are directly measurable in the current census. The result is a family of worlds whose fates may be driven by dynamos that instruments can only infer from subtle asymmetries in spectra or from the presence of auroral lines that push the frontier of detection. The paradox of knowledge thickens. The more traits are measured, the more crossroads appear. The planets refuse to be averages. They are particulars. A percent more envelope, a whisper more light from the star, a slightly different hour in the birth of the disk, and the climate flips, the density shifts, the escape rate doubles or halves. The cloud becomes mirror instead of shroud. The wind carries heat or hoards it. The same silhouette contains a dozen meteorologies and 3 different lineages. The mystery intensifies not because evidence is thin, but because evidence is abundant and contradictory in ways that only precision can reveal. The escalation feels like the deepening of a melody rather than a change in key. Each new instrument brings harmony and dissonance together. The worlds keep their counsel, the telescopes keep their vigil. The data sharpen the outlines while multiplying the possible interiors and histories. It is not confusion. It is richness at the edge of what distance allows. The lesson is patient and unsentimental. These planets are common, yet none of them is generic. Understanding will not arrive as a single answer. It will arrive as a map with many paths, where the shortest line between size and nature is a curve that passes through clouds, through stars, through time. The central ideas grew into a small constellation of theories, each lit by equations, and each ringed by speculation. They did not compete like enemies. They circled the same puzzle from different distances, and tried to name the invisible forces that sculpt a world between rock and giant. At their heart lay a simple contest. A young planet gathers what it can. Time and energy decide what it keeps. To understand the result, the theorists built stories about heat, light, wind, and the choreography of growth. One idea looks outward first. A close planet lives under a lamp that never blinks. High-energy photons split molecules in the upper air and heat the thin gas until it moves faster than escape speed. What begins as a hot breeze becomes a persistent outflow. Hydrogen slips away first, then helium, then atoms that ride the flow like dust in a current. This is photoevaporation. It is not spectacular when watched on the scale of an hour. It is relentless when watched on the scale of 100 million years. A small difference in the brightness of a star or in the gravity of a planet sets a boundary between envelopes that survive and envelopes that depart. The boundary is sharp enough to build a valley in size. The math is severe and the picture is clean. The planets that keep their air have crossed a threshold early. The planets that lose it are shaped by light like cliffs carved by weather. Another idea looks inward. A planet is born warm. Accretion is a violent arithmetic that turns motion into heat, and radioactive elements add a quiet furnace. Even without a fierce star overhead, the stored energy must climb through the envelope. If the envelope is thin, the escape becomes easier as the gas puffs and cools from the top. This is core-powered mass loss. It suggests that the planet edits itself from the inside, exhaling until the heat ledger balances. The outcome is sensitive to the thickness of the envelope at birth. A few percent by mass can be shed, leaving a compact body that looks rocky. A thicker skin can resist the exhale and linger as a soft-edged world. The idea is attractive because it gives agency to the planet rather than to the star, and because it can operate far from intense light. A third idea ties fate to migration. A young disk of gas and dust behaves like a river with rules. Cores grow where solids gather. They drift as torques between disk and planet exchange momentum. Some move inward gently and park near the star. Others stall at pressure bumps where disk winds have opened cavities. If a core reaches a critical mass while the disk still feeds, it can accrete a deep envelope and become a sub-Neptune. If it misses the window by a few 100,000 years, the gas will thin and the same core will end as a super-Earth with only a modest sky. Timing becomes destiny. The valley appears not as a cut made by loss, but as a gap left by the schedule of supply. A related view invokes pebbles. Centimetre-sized solids drift inward through the disk and are swallowed efficiently by growing cores. The rate of this pebble accretion sets the clock for crossing thresholds. Rich pebble flows let many cores reach the mass that captures gas. Weak flows starve them. The distribution of pebbles changes with distance from the star and with the life of the disk. Theories in this family can paint a picture where the most common worlds are simply the ones that had time to grow a little, but not enough to trigger runaway gas capture. They sit in a mass band that turns small choices into large differences in radius once the envelope settles. Water worlds offer another path. Cores that assemble beyond the snow line inherit large shares of ice. If such bodies migrate inward, while the disk still shields them, they can live in warm orbits with deep mantles of high-pressure ices that behave more like minerals than like sea. A thin layer of supercritical fluid can sit above, and a compact atmosphere can ride on top. The radius swells even without much hydrogen or helium. The chemistry of the upper air will then reflect the scalded interface between fluid layers and starlight rather than a dry basaltic crust. The presence or absence of a taste for water in spectra becomes a subtle verdict on where a world learned to build itself. Catastrophe makes an appearance. After the gas clears, planets can collide. A head-on strike can blow off an atmosphere like dust from stone. A glancing impact can strip volatiles asymmetrically and leave a tilted core. Energy from such encounters can keep a world puffed longer than its age would suggest. The mismatched siblings that orbit the same star may remember different impacts rather than different births. Giant collisions also rework interiors, redistribute iron and silicate, and reset magnetic dynamos that shield atmospheres or stir them to loss. A population shaped by many small tragedies will not sort neatly by distance from the star or by present mass alone. Outgassing provides a quieter counterweight. Volatiles trapped in minerals and ices can rise over time through volcanism or through metamorphic reactions at depth. Even a planet that lost its first envelope can build a second. The composition will differ. Hydrogen will be rarer. Heavier molecules will mark the air. Pressure at the surface can still climb to the point where water behaves like a supercritical fluid and where carbon chemistry writes a climate that is slow to change. If outgassing competes with escape, a world may hover near the threshold where the valley lies, sometimes swelling with new air, sometimes shrinking as sunlight steals it. Disk wines enter as sculptors of the nursery. Magnetic fields thread the gas. They drive outflows that peel mass from the disk and reshape pressure profiles. Where pressure peaks gather, drifting solids pause and pile up. Where the gas thins, migration slows. Planets then find parking spots that are not obvious in smoother disks. A ring structure can feed some embryos while starving others only a few tenths of an astronomical unit away. The initial map of cores becomes lumpy, and the envelopes each core can win become more sensitive to small offsets in place and time. In such a picture, the valley arises because the birthplaces are not equal, and the step from thin air to fat air is crossed in a hurry where supply changes abruptly. Opacity and metallicity turn the gas itself into a decision-maker. An envelope rich in heavy molecules cools differently than a clean hydrogen-helium mix. Higher opacity slows contraction. Slower contraction keeps the radius larger for longer and makes the atmosphere easier to erode by light or by the planet's own heat. A lower opacity allows the envelope to settle quickly, deepening the gravitational well and making escape harder. Since envelopes inherit their mix from the disk and from accreted ices, chemistry at birth leaves fingerprints on survival without any change in mass or orbit. Two planets of the same weight can diverge because one breathes air that is cloudy with metals, and the other breathes a sky that radiates cleanly. Electric currents whisper from the upper atmosphere. A wind that moves through a magnetic field can induce currents that deposit energy deep in the envelope. This ohmic heating has been invoked for larger planets and may have a milder but still important role here. If the air is partially ionized, the dayside breeze can feed the nightside with electrical warmth. The result is a planet that refuses to shrink as quickly as its age demands. A small nudge of heat, applied for a long time, changes the radius enough to move a world from one side of the valley to the other in the statistics. tides, need interiors, and write footnotes in the energy budget. A slightly eccentric orbit around a low-mass star can flex a planet each time it swings through periastron. The flexing warms. The warmth slows contraction or sustains volcanism that feeds the sky. In compact systems, the tug of neighbors can keep the eccentricity alive for billions of years. The secret heat then becomes a quiet sponsor of thick air, where a simpler model would predict loss. The same process can also dampen rotation and tilt, adjusting circulation in ways that alter cloud formation and chemistry at the limb sampled during transits. Speculation reaches for life because the mind is built to ask. A hydrogen-rich sky can act as a greenhouse, even far from a star, raising surface temperatures on worlds that would otherwise freeze. If an ocean lies below, chemistry can begin in environments unknown to Earth. Biosignature gases would not look familiar. Methane would be common from non-living sources. Oxygen would be rare without special paths. Other molecules, like nitrous oxide or dimethyl sulfide, might travel poorly through hydrogen air and hide. The search would depend on combinations rather than on simple flags. The likelihood of life remains a gentle unknown, but the stage it would require is no longer exotic. Each theory survives by making testable promises. Photoevaporation predicts that younger stars carve deeper scars. Core-powered loss predicts that planets of similar mass will tell different stories at similar irradiation. Migration stories predict resonant chains with subtle offsets. Pebble accretion predicts correlations with stellar metallicity and with disk substructure seen around newborn stars. Water world scenarios predict atmospheres that taste of steam and volatile rich chemistry even when hydrogen is scarce. Impact stories predict scars in obliquity and in density contrasts between neighbors. Outgassing predicts that some bare cores carry heavy skies where escape cannot remove them quickly. The promises overlap. That is why the sky must be read in many languages at once. Speculation does not float free of discipline. It flowers along the borders set by data. The ideas above are not mutually exclusive. In one system, starlight may be the sculptor. In another, interior heat may be the editor. In a third, the disk may have set a witness mark that never faded. The class of intermediate planets is wide enough to host all of these fates. The task is to weigh their shares and to learn which stories nature preferred most often. The path to that answer will pass through more precise masses, cleaner spectra, and long watches that capture the small drifts of timing that betray hidden neighbors. In the meantime, the theories stand like instruments tuned and waiting, each ready to play when the data lift the conductor's hand. The instruments say little and prove much. They harvest faintness and translate it into pressure, wind, and chemistry. In orbit, a telescope tuned for the red heat of worlds opens its segmented eye and turns starlight into rainbows. The spectra it gathers are written in a script of valleys and ridges, each feature a note struck by a molecule, each absence a silence kept by cloud or haze. During a transit, some of the light grazes the planetary limb and carries the taste of its air. During an eclipse, the world slips behind its sun, and the missing glow reveals the planet's own fire. Between these moments, phased light curves draw slow maps of day and night. From such pieces, climates are inferred, molecules counted, and winds assigned to invisible skies. Closer to Earth, an aging sentinel of mirrors measures subtle colors during occultations with patient precision. The measurements are not loud, they deepen confidence. A quiet bump in the near-infrared becomes the trace of vapor. A flattened swath becomes evidence for high condensates. Orbital campaigns repeat, stacking transits like breaths, until the noise surrenders a pattern. The discipline is ritualistic. Exposure times, calibrations, reference stars, all obey strict routines that turn photons into arguments strong enough to withstand doubt. On the ground, spectrographs built like vaults hold air at constant temperature and pressure. Their optics anchored to granite or floated on damp tables. They listen for the heartbeat of stars. A shift of a meter per second in the stellar spectrum, A few atoms' widths of drift becomes the weight of a world. When several planets share a system, the rhythm overtones blend, and careful analysis teases them apart. Another set of spectrographs work at much higher resolution to separate planetary lines from stellar lines through cross-correlation. A faint, moving forest of absorption lines can be dragged into view and matched to templates for water, carbon monoxide, or other gases. The planet's orbital speed leaves a diagonal scar across time that becomes an independent confirmation of atmosphere and circulation. Timing has its own instrument. Arrays of small telescopes dot mountain tops and deserts, sharing the sky region by region. They watch transits with minutes of cadence and record small departures from perfect periodicity. Gravitational nudges between neighbors create delays and advances measured in seconds. Those drifts can weigh planets that no spectrograph can reliably lift from a noisy star. The pattern of departures also encodes orbital eccentricities and mutual tilts. Over years, the timing archives become a ledger of interactions, revealing hidden companions and measuring the elasticity of compact systems. Light itself can be caught in two moods. Reflected starlight in the optical tells of clouds and surfaces. Thermal emission in the infrared tells of heat budgets. Instruments separate the two and follow them around an orbit. Brightness builds to a crest as dayside turns toward the observer, then slips as night returns. The phase of the crest relative to the eclipse reveals winds that push heat eastward or leave it central. A displaced hotspot sketches a jet stream. A centered blaze sketches sluggish air or deep radiative layers. Slowly, the sketches accumulate, and circulation models either earn trust or learn humility. Stars must be known with similar care. Astroseismology treats them like resonant spheres. Tiny pulsations ripple their light. From those ripples come densities, radii, and ages more precise than broad catalogues can offer. Gyrochronology adds the spin of stars as a rough clock. Chromospheric indicators monitor magnetic weather. Photometric spot maps chart rotation periods and activity cycles. All of these reduce the stain of astrophysical noise on planetary spectra. They also adjust the dates on the planetary calendar, turning guesses into birth certificates with error bars that shrink. In laboratories, materials are pushed to planetary conditions. Diamond anvil cells crush water, and silicates into states that refuse common names. Lasers drive shock waves through fluids to emulate the pressures of deep mantles. Opacity tables for exotic mixtures are revised after each experiment. Reaction pathways for photochemical haze are measured under ultraviolet lamps in chambers filled with hydrogen, methane, and nitrogen. The residues, tarry or pale, teach retrieval algorithms what to expect when light passes through such aerosols. Equations for how gas escapes from the top of an atmosphere are tested against supersonic expansions and vacuum chamber flows, then folded back into models of loss driven by starlight or interior heat. Supercomputers tie pieces together. N-body codes follow embryos in a young disk as they collide, accrete, and migrate. Hydrodynamic simulations make the gas in the disk push and pull on those embryos and open gaps that arrest or accelerate their drift. Global circulation models run atmospheres under bright suns, predicting jet streams, cold traps, day-night contrasts, and the formation of clouds along particular latitudes. Radiative transfer engines work in tandem, translating temperature and composition into spectra a telescope expects to see. Retrieval frameworks move in the opposite direction, starting with measured spectra and climbing back up to the most likely mix of molecules, clouds, and temperatures. The frameworks lean on Bayesian logic, mapping where the probabilities settle rather than chasing single best fits. Every iteration tightens the weave between observation and theory. Long baselines are the most uncompromising tool. A decade of transits recorded for a single system will show drifts that a season hides. Orbits that look circular at first may reveal slight eccentricities. Resonant angles may librate. Transit duration variations will betray slow nodal precession. All indicate mutual tugs, hidden companions, or tides at work. Mass estimates improve, densities sharpen. The same commitment reveals stellar cycles that masquerade as planetary signals. A spotless year might give way to a mottled one. Calibrations are adjusted and conclusions updated, not for drama but for accuracy. Even the dark between targets is used. Choice itself is an instrument. The brightest host stars become prioritized because they turn every photon into more leverage. The most temperate planets rise in rank because their chemistry sits near the margins where life's preconditions could exist. Ultra-short period worlds are studied as controlled extremes, their rock vapor atmospheres and lava seas acting as laboratories for mineral weather. Multiplicity is courted when architectures can test migration and resonance. Solitude is courted when clarity is needed for atmospheric probes. The queue of observations becomes a living experiment, refined after each result to press on weaknesses in prevailing models. Testing reaches beyond sight. Magnetic fields are hunted indirectly. A sliver of polarized light in the optical, a faint signature of cyclotron emission in the radio, or a spectral line broadened unexpectedly may imply a dynamo churning below. If confirmed, such fields would change escape rates, wind patterns, and the resilience of atmospheres under stellar tempests. Seismology of planets remains a dream, but glimmers appear in transit timing if tides shift interiors. Gravitational measurements at microarcsecond precision, promised by astrometric advances, would weigh planets without relying on stellar jitter and help cross-check all other methods. Prototypes of future coronagraphs take shape inside clean rooms where light is trained to cancel itself. Masks and deformable mirrors carve diffraction into darkness, making space for the faint reflection of a planet near a star. Even if only the largest intermediate worlds around the nearest stars become visible, phase-dependent spectra from such direct views would free the measurements from the contaminating backlight of the stellar disk. The technology is disciplined by testbeds that measure contrast 1,000,000,000 to 1 and educate the next generation of space telescopes. In parallel, arrays of ground-based telescopes, vast and segmented, prepare to combine huge collecting area with adaptive optics that erase atmospheric blur. They will split starlight finely enough to follow winds on distant worlds by tracking Doppler shifts across a rotating disk. Collaboration is the invisibly essential instrument. Spacecraft relay targets to spectrographs. Spectrographs post masses for retrieval teams. Modelers flag degenerate solutions and suggest new wavelengths to break them. Observers build campaigns that mix optical and infrared, space and ground, short cadence and long. The chain of custody for a single world can include a survey detection, a network of small telescopes for confirmation, a large telescope for weight, a space telescope for atmosphere, and years of follow-up to refine time. At each link, the result is archived, reprocessed, and made ready for strangers who will ask new questions of the same photons. In the end, the ongoing testing looks like patience organized. There is no single decisive experiment, no unique instrument that renders all others decorative. Progress arrives as a slow braid of methods. Spectra deepen, clocks extend, simulations widen, laboratory constants harden. Every thread fortifies the others. The planets under study do not grow nearer, yet their anonymity thins. Clouds become quantifiable veils rather than excuses. Heat budgets become measured flows rather than metaphors. Winds begin to own directions and speeds in maps that nobody has seen yet everyone can justify. The result is a science that treats distance as a solvable inconvenience. The worlds remain remote. The tools are intimate. The idea arrives as a quiet tide. Somewhere around a dim star, a planet larger than Earth carries an ocean without a shore. No continents break the surface. No islands rise to catch light. The sea climbs down and down until pressure turns water into unfamiliar states that hold no memory of rivers or rain. High in the air, a veil of hydrogen sits like a lantern glass, trapping heat with a patience that can keep the surface from freezing, even at distances where sunlight is thin. The world is neither a giant nor a garden. It is an ocean wrapped in light air, and it keeps its own counsel. At the interface between sky and sea, chemistry begins to speak a new dialect. Sunlight breaks molecules in the hydrogen-rich air and lets them recombine into families that do not dominate temperate skies on rocky planets. Methane rises and shifts. Ammonia leaves fingerprints when the light is gentle and fades when the light is harsh. Water vapor slips upward from beneath and fights to keep its signal unmuted. Photochemical hazes can grow grain by grain into a diffuse ceiling that both shields and obscures. To instruments, the scene is either eloquent with bands and troughs or almost mute, a spectrum sanded smooth by aerosols. To the planet itself, the haze is weather, born out of the balance between sunlight and uplift, between condensation and mixing. Beneath that thin hydrogen veil, the sea is not Earth-like. Surface waves blur under heavy air. No salt spray rides the wind for long. The pressure at a few hundred meters equals that of deep trenches on Earth. A few kilometers down, new phases of water appear, crystals that squeeze into forms called Ice 6, then Ice 7, ending in phases that are less a mineral than a cage of atoms forced into intimacy. Heat from the planet rises through this stack. Where the pressure permits, water becomes supercritical and forgets the difference between liquid and vapor. If the planet once held a rocky core rich in iron and silicates, that core now sits under a blanket of ice so dense that it behaves as a mantle. The boundary between sea and stone becomes a laboratory for reactions that have never seen air, with minerals meeting water at conditions that rewrite their names. In such an environment, continents are an extravagance that never happen. Weathering is not a long dialogue between rain and granite. Nutrients are not cycled by rivers marching to a shoreline. If elements vital to chemistry are to circulate, they must travel through vertical exchange. Hydrothermal vents at the ice-rock interface can rise as plumes into the deep, scattering metals and sulfides into the supercritical darkness. The sea above can convect, stirred by heat at its base and by winds at its top. The hydrogen lid slows the loss of heat to space and stretches the timescale for turnover. Each layer finds a tempo, slow for deep mantle ice, faster for supercritical fluid, faster still for the mixed ocean where sunlight, if any reaches, fades into a green that soon gives up to black. The greenhouse power of hydrogen shifts the map of habitability. A world like this can hold liquid water where a rocky planet would glaze. The gift is double-edged. The same light air that warms can also escape under the battering of starlight, and replenishment is not guaranteed. If the planet began with a generous envelope taken from its birth disk, the envelope may survive for billions of years, especially if the orbit sits far enough from the star to ease the ultraviolet assault. If the planet began lean, the lid may thin and the ocean cool until the phases deepen and the sea becomes a frozen mantle. The difference between endurance and loss can be a few percent in envelope mass, a small tilt in orbit, a faint shift in the star's temper. Tides need such a planet into motion. A slight eccentricity under a small star can keep the interior warm long after formation heat should have faded. The heat powers vents, alters convection, and might even puff the hydrogen lid enough to change escape rates. In a chain of neighboring planets, resonances can pump this eccentricity steadily. The sea that looks still from the outside can shiver through with slow internal waves that drift for days and crest in places where chemistry gathers. The geometry is simple, the consequences are not. If life ever draws a map here, it will mark oases not by latitude or climate zone, but by the quiet fireworks of geology in the dark. Observation chases clues that carry the taste of such oceans without revealing their surfaces. A strong water vapor signature, in a world that is not too hot, whispers of a deep reservoir below, even if no glint of reflection is seen. A balance between methane and carbon dioxide can hint at the depth of atmospheric mixing and at the presence of a liquid interface that sets chemical ceilings and floors. Ammonia that lingers suggests cooler air and shielding from harsh light. Sulfur-bearing compounds would point to vent-like processes, though the path from vent to sky is long and winding. No single molecule crowns the case. The case is a chorus sung across wavelengths. If life takes root, its language will differ from Earth's. Hydrogen air would erase some familiar flags and amplify others that are rare at home. Oxygen made by sunlight would not accumulate without constant renewal. Methane could be common from non-living sources. Nitrous oxide might survive poorly through the hydrogen lid. More exotic compounds, fragile in oxygen-rich air, could travel farther here. The search would be statistical and contextual, the negative space around combinations telling as much as the presence of any single gas. The promise feels audacious, yet not fanciful. Oceans want chemistry, and chemistry wants gradients. This planet type supplies both in abundance, even if the gradients run between vent and sea rather than between continent and cloud. Clouds decorate the lid in seasons that are set by orbital geometry rather than by continents. If the planet leans in tilt, bands of haze brighten or darken with the path of the star. If the orbit is almost circular, storms will gather at the substellar point where updrafts are strongest, leaving night to clear and radiate. The phase curve carries these stories in delicate shifts of brightness. An eastward displacement of the hot region marks a jet. A westward one marks drag that fights winds in the upper air. Thin clouds make room for water lines to rise. Thick clouds lower the contrast and turn the signal into a riddle. The riddle is a kind of answer because it tells that weather is present. Salt has a different role. Without continents, salts are delivered not by rivers, but by the churning of the ocean against the mantle ice and by the leaching of minerals near vents. The result can still be a brine. Its composition will not copy Earth seas. It will depend on the rock below, on the heat above it, and on the age of circulation cells that link deep to shallower layers. This chemistry meets starlight only if upwelling carries it to the surface. If not, it remains a submerged world of flavors and metals, a memory held in water phase diagrams rather than in shorelines. Even the color is conjecture. A hydrogen sky can scatter blue light and paint the dome pale. A haze made of complex hydrocarbons can dim that blue to copper. If clouds sit high and wide, they might present a bright face in optical light, a reflective shield that hides the sea beneath and makes the world cooler than it would otherwise be. If clouds sit low and patchy, the sea can drink light and radiate warmth in infrared bands that shift with humidity and wind. Instruments that separate reflection from emission can sketch this palette with enough patience. The sketch is not a photograph. It is a portrait made from a handful of colours, chosen carefully. Formation paths to such oceans are not singular. Some cores grow beyond the snowline, drinking ices and drifting inward until the disk thins. Others collect dry rock first, then accrete water-rich debris, later through a hail of minor bodies. If the hydrogen lid becomes too thick, the world swells into a puffy sub-Neptune with deep air and a sea that may never see starlight. If the lid is too thin, the world becomes a rocky super-Earth with lakes or seas that cover less than a global face. Between these outcomes lies a slender corridor where an ocean can rule and a light atmosphere can warm without dominating. The corridor appears narrow, yet it is travelled often enough that catalogues keep its name on many pages. In that corridor, night would sound different. Waves would fall with the weight of a heavier air. Lightning, if present, would strobe through fogs that never fully lift. No bird would wheel above. No leaf would toss and flash. The poetry belongs to the physics. Hydrogen air, deep water, crushed ice that behaves like stone, vents that glow with heat made from tides and time. The picture is alien without cruelty. It is hospitable without resembling the template that nurtured thought on one blue world. This vision does not ask for belief. It asks for attention. The measurements that hint at it are testable and will be tested again. The chemistry will be probed at more wavelengths. The phase curves will be watched over more orbits. The masses will be weighed with finer tools. If the oceans are there, they will continue to lean on the spectra. pushing water lines up through noise, muting or brightening bands with weather. If life is there, it will speak softly and indirectly, in ratios and absences. The task is to learn to hear whispers carried across the light years. Fate can hinge on air that weighs almost nothing. A thin veil of hydrogen and helium, only a few % of a planet by mass, can lift a radius into a new category and hold heat long after youth has passed. A slightly thinner veil can slip away under light and time, turning a swollen profile into a compact shape that hides its past. The physics lives in margins that humans can barely feel with their hands, yet that carve valleys and build peaks in distant statistics. To see the path, one must follow the breath of a world as it exhales across eons. At the top of the sky, gravity and heat keep a quiet negotiation. Temperature sets how fast particles move. Gravity sets how fast they must move to leave. Hydrogen is light and quick. Helium is heavier and slower. If photons from the star pour enough energy into the upper layers, the atmosphere can flow outward like a gentle fountain, not a storm, but a persistent departure. The flow thickens where molecules absorb ultraviolet light and thin to atoms. In that region, collisions trade energy between species. Hydrogen drags heavier companions if the flux is strong, a shared escape that leaves fingerprints in chemistry. Far below, the denser air sits unaware, yet over ages the loss from the top draws on the reservoir beneath. The atmosphere becomes a river whose source is the mantle of gas and whose mouth is space. The river does not run at one speed. Early in a planet's life, high-energy radiation from a young star glows like a forge. Escape is energy limited, paced by how fast the star pumps power into the upper air. Later, as the star quiets and the planet cools, the flow slows. The regime shifts toward one controlled by diffusion and by the slow climb of the lightest molecules through a mix of heavier ones. In this quieter era, the atmosphere can settle into a long plateau where loss continues but no longer threatens to erase the envelope quickly. The line between eras is not sharp, yet the memory of that early rush can decide whether a world becomes bare or remains softly wrapped. Cooling at depth changes the game again. While the upper layers face the star, the interior bears its own clock. As formation heat leaks outward and radioactive elements cool, the envelope contracts. Contraction deepens the gravitational well, lowering the scale height of the gas and tightening the grip on the top. A world that survives the first 100 million years with its veil intact can cross into safety as its radius shrinks and escape speeds rise. This is why a difference of a few % in initial envelope mass matters. A little more gas can buy enough time for contraction to fortify the planet against later loss. A little less leaves the world exposed long enough for the star to finish the job. Metal content adds a subtle lever. Hydrogen and helium are transparent in many bands, but traces of heavier molecules increase opacity, slowing the escape of heat from the envelope. Higher opacity holds a planet swollen for longer, making early escape easier. Lower opacity lets the planet compact quickly, which is protective but also reduces detectability from a distant telescope. The chemistry of the envelope therefore decides the tempo of contraction and the vulnerability to stripping. Two planets of the same mass and orbit can drift toward different fates if one breathes a slightly murkier air. Winds inside the envelope carry heat and composition along paths that shape the loss. If the upper atmosphere ionizes, moving gas across a magnetic field generates currents that deposit energy deeper than sunlight alone can reach. Ohmic dissipation softens contraction and keeps the radius larger. If the magnetic field lines open to the stellar wind, charged particles can ride out along them, easing escape along polar routes. A strong dynamo can deflect some of the wind and reduce direct sputtering, while also inviting energy input that puffs the upper layers. The balance is delicate. The same shield that protects can also feed the furnace at the edge of space. The structure of the envelope stratifies into layers with distinct loyalties. A deep convective zone moves heat efficiently, carrying entropy upward like freight on an elevator. Above it, a radiative zone insulates, letting energy leak only by the slow diffusion of photons. The boundary between them slides with age, composition, and irradiation. A thicker radiative lid delays cooling and prolongs vulnerability. A thinner lid lets the planet settle. Clouds and hazes complicate the radiative balance by reflecting starlight and absorbing at favorite colors. Their presence can cool or warm different levels, moving the boundaries and rewriting escape rates without changing the mass below. Volatile supply at birth sets the stage. A core assembled near the snow line arrives rich in ices and easily captures a light envelope if the disk still breathes gas. A core born closer to the star may need to grow faster or wait for migrating pebbles to deliver ices later. If the disk disperses before the core reaches the mass needed to bind a thick veil, the newborn planet wears a sky so thin that later outgassing from its interior might rival the original. That secondary atmosphere will smell of heavier molecules, carbon dioxide, and nitrogen rather than hydrogen and helium. It will be tougher to blow away, but it will not lift the radius into the puffy regime. The world will remain compact, not because escape triumphed, but because supply ended sooner than capture could accelerate. Collisions rewrite envelopes in an instant. A late impact can strip a half-formed sky without touching the interior. Another can stir the mantle and feed a burst of outgassing that rebuilds a thinner, heavier air. The statistical imprint of such events appears when neighboring planets show starkly different densities despite similar orbits. The veil here is not a passive blanket. It is a ledger of violence and repair. The same planet might pass through several identities, puffy with light gases, bare and bright, cloaked again in heavier breath from within. Each phase carries its own climate and sets its own path toward the future. The slow exhale has geography even at constant distance from the star. High latitudes can vent more easily if magnetic field lines open there. The substellar point can drive stronger upwelling and loft photochemical products higher, where they either absorb more energy or cool the gas by re-emitting in infrared bands. Nightside regions, if circulation is sluggish, can harbour cold traps that condense species into clouds or frost, changing the overall composition available to escape. The envelope becomes a living system with feedbacks. Remove a little hydrogen, and the mean molecular weight rises, shrinking the scale height and slowing further loss. Add metals from outgassing, and opacity rises, delaying contraction and encouraging loss in the next season of stellar activity. The speed of change itself changes. There is an austerity to the numbers. For small envelopes, a few tenths of a percent in mass can lift a radius by several percent. That lift pushes the planet into a larger cross-section during transit, making detection easier and the target more tempting for atmospheric work. Yet that same lift makes the surface gravity on the topmost layers lower, and the escape more efficient if the star is bright in high-energy light. The geometry of discovery and the physics of erosion lean in the same direction, favouring the study of planets that live near thresholds. Many of the most interesting cases reside precisely where air can be won or lost with modest pushes. Heavy elements infiltrate the veil in ways that trace ancestry. If ice is dissolved into the envelope during assembly, the air can begin life metal rich. If the envelope accreted quickly from clean nebular gas, it can begin metal poor and gradually enrich as heavier molecules leak upward from below. The path matters for climate. Metal-rich air radiates differently, forms clouds at different heights, and couples more strongly to light. Metal-poor air cools faster and may resist haze formation under similar irradiation. Observations that catch water, methane, or ammonia in transmission offer hints at this inventory, but the upper layers alone cannot tell whether the deep envelope shares the same taste. Dice equilibrium chemistry, set by mixing and by photolysis, is a reminder that a snapshot of the limb is not a full portrait of the column. Over very long times, the envelope can approach fixed points. One such point is full loss for light gases, where only heavier molecules remain and escape slows to a geological crawl. Another is a stable fraction of hydrogen and helium sustained by interior cooling that has fallen nearly to zero and by a star that has aged into quiet. Planets that reach the latter point become time capsules. Their present skies are fossils of their birth conditions, modulo early erosion. Planets that reach the former point become laboratories for secondary climates, their temperatures and pressures humming to rhythms set by greenhouse gases heavier than hydrogen. Between these points lies a broad plain where small adjustments in irradiation or composition can tip a world from one fate toward the other. From a human distance, it is tempting to make moral stories out of this physics. Thin veils seem fragile, thick veils resilient. Yet survival is not virtue, it is arithmetic. A little more gas at the start, a slightly dimmer star in youth, a quicker contraction, a collision that tilts probabilities rather than erases futures. The outcomes feel fated only in hindsight. In the moment, each planet is a calculus problem run forward through heat and light, through gravity and time. The veil is both variable and decisive, a small part that determines the whole. For a listener who wants a single image, picture a candle under a bell jar. If the jar is high and wide, the flame will dance for a long time, its heat swirling in patterns that reshape the air. If the jar is low and thin, the flame will gutter quickly, then leave a warmth that fades through glass. Replace the candle with a planet's interior and the bell jar with hydrogen sky. Replace the air in the room with starlight. Time will choose which jar remains and which shatters. The details of thickness, opacity, and cooling decide how the dance begins and how it ends. The new eye in deep space opened like a held breath released, and the first spectra felt less like data and more like weather written in light. Mirrors of gold gathered the faint warmth of distant worlds, then sent it through instruments tuned to the colours where molecules speak most clearly. Lines for water rose in the near-infrared. Carbon dioxide etched a deep cut at longer wavelengths. Methane, slippery and shy in earlier work, stepped forward in bands that instruments on the ground and in low orbit could barely touch. The effect was immediate. Planets that once looked like silhouettes acquired climates. Skies that had seemed mute began to answer questions with a grammar of ridges and valleys. Transmission became the opening movement. During a transit, a sliver of starlight grazes the limb of a planet and carries the taste of its air. The new spectrographs spread that sliver into colours from the red edge of visible to the heart of thermal infrared. Where earlier telescopes saw flattened features, the new instrument found structure rising above the haze. Water cut a repeating pattern, a signature that stacked with each orbit until noise surrendered its disguise. Carbon dioxide sculpted a broad feature that anchored retrievals and stabilized inferences about metallicity. Methane declared itself in cooler targets around small stars, altering expectations about quenching and mixing. Oxygen-bearing species other than water remained elusive, and that elusiveness was information of its own. Eclipse spectra followed. When a planet stepped behind its star, the missing light in infrared revealed the dayside glow alone. The curves across wavelengths showed temperatures that were not guesses but measured surfaces of air, thousands of kilometers wide. Some worlds radiated like black bodies with only gentle slopes of color, a sign of deep, nearly featureless photospheres. Others showed modest absorption by water and carbon monoxide, hints that their upper layers were not isothermal, but carried gradients that theory had proposed long ago. On a few, brightness lurched in ways that implied patchy clouds, dark regions that winked out at eclipse and bright ones that remained to draw the lines. Phase curves became maps. The dayside rotated into view, peaked and sank, while the night side took its turn with a hush of heat. The time of the peak, shifted eastward from the substellar point on some worlds, announced a jet that carried warmth downwind. On others, the peak stayed nearly fixed, suggesting drag in the upper atmosphere or radiative layers too deep to move heat quickly. The night side glowed more on some than expected, less on others. In one case, the pair of hemispheres differed by almost 1,000 degrees, a sign that the air was thick yet stratified. In another, the difference softened, a sign that wines punched through the radiative lid and stirred layers together. The patterns were messy, and within that mess lived a new kind of clarity. Clouds stopped being an excuse. With long wavelength reach, the instruments climbed above the thinnest aerosols and peered into windows where absorption by molecules had fewer competitors. Where spectra flattened at shorter wavelengths, they began to show teeth in the mid-infrared. Particle sizes could be inferred from slopes. Compositions could be constrained when features aligned with condensates expected in warm hydrogen air, sulfides where the temperature fit, salts where the chemistry allowed. A planet that used to be mocked as featureless became simply overcast, then became quantifiably overcast, a weather diagnosis rather than a shrug. Metallicity stepped forward as a measurable trait. Water and carbon dioxide features fixed the relative importance of heavy molecules in a light envelope. Combining them with mass and radius, retrievals produced abundance ratios with error bars small enough to matter. Some worlds showed air more metal-rich than predicted for their weight, a hint that ices and rock contributed heavily to their envelopes during assembly. Others leaned metal-poor, consistent with accreting cleaner gas late. Carbon to oxygen ratios inches away from stellar values appeared in a few candidates, whispering of birth zones relative to the water ice line. Each inference arrived wrapped in caveats, but together they pushed formation stories from speculation toward audit. Thermochemistry and photochemistry found a negotiator. The spectra showed methane present on some temperate sub-Neptunes where earlier work had hinted at scarcity. On hotter cousins, methane faded and carbon monoxide dominated, a neat match to equilibrium expectations. Yet, at intermediate temperatures, the lines did not obey simple boundaries. Quenching by rapid vertical mixing seemed to freeze compositions from deeper, warmer layers into the observable heights. Photolysis high in the sky created radicals that built haze precursors and lowered the contrast of features. The balance changed with stellar color. Around redder stars, the ultraviolet that drives haze was gentler, and more molecular structure survived. Around more active stars, the upper air behaved like a refinery for soot. Instrument design showed its wisdom in the way the pieces corroborated each other. One channel held a stable baseline across a tricky band, useful for breaking a degeneracy between clouds and composition. Another delivered high resolution around a single feature that acted as a linchpin for abundance. A third extended to wavelengths, where the planet's own emission began to dominate, setting temperatures that disciplined all other conclusions. Cross-calibration between channels was not a luxury, it was a method. When independent slices of spectrum implied the same water abundance or the same opacity flaw, the inference could stand. When they disagreed, the team returned to the raw pixels, and the sky was granted more time. Targets became characters with distinct voices. A warm, low-density world around a small star wore a high haze but still let water lines through in the mid-infrared, a soft-spoken spectrum that nevertheless shaped the narrative about cloud decks. A slightly larger cousin, bathed in gentler light, revealed methane and carbon dioxide together, a combination that made ocean-covered interiors feel plausible while keeping the verdict tentative. Another, hotter and more inflated, showed evidence of vigorous day-to-night winds, a night side not as cold as expected, and clouds that formed at longitude seasonal weather on Earth would never consider. None of these were trophies. They were baselines, the new normal for a class once known mostly by radii and periods. The instruments also taught caution. Stellar contamination does not vanish at higher sensitivity. Spots and faculae on the host can still stain the cord a planet samples during transit. Calibrations preserve or destroy tiny slopes that turn into big differences in retrieved abundances. Systematics that drift on hour timescales can mimic muted features. The teams built elaborate ritual around these risks, repeating visits, toggling instrument modes, sharing pipelines between groups that did not share assumptions. The reward was not headlines, It was cleaner posteriors, parameter spaces that shrank honestly. Escape physics learned new notes. While the most dramatic signatures of helium outflow remain easier to catch at specific near-infrared lines from other facilities, the long wavelength reach helped close a loop between upper atmosphere heating and lower atmosphere structure. Planets with hotter thermospheres tended to carry evidence for increased metallicity below, a pattern that fit models where photochemistry seeds haze that both absorbs and shields. In some targets, faint continuum absorption at long wavelengths hinted at cloud decks of unusual composition, the kind that form only when escape has already gnawed away the lightest gas and left a heavier mix above. Interior models were forced to adapt, with metallicity estimates in hand and temperature profiles that were not guesses. The inferred fraction of hydrogen and helium in an envelope could be narrowed. Some planets that once sat comfortably in the category of water worlds moved toward the territory of thin hydrogen skins on rocky cores. Others travelled the opposite direction, their spectra telling of atmospheres too heavy to be mere caps, more likely the upper reach of deep volatile mantles. The radius valley did not disappear, but the boundaries around it acquired texture. The sharp cut in size could now be traced through composition, a separation not only of radii but of air and interior. The logistics of time turned into a science of its own. The observatory cannot linger indefinitely, so teams learned to braid goals. A sequence might catch a transit for transmission, remain on target long enough to secure the eclipse, then ride the declining light for a good stretch of phase curve. Such braids maximized insight from scarce hours and reduced vulnerability to uncooperative stars. Seasonal windows for targets near the ecliptic poles allowed repeated visits that built signal to a threshold where subtle features cleared the horizon of noise. Patience, aggregated across a community, made the new knowledge feel inevitable. The summary belongs to the senses. The observatory did not merely increase sensitivity, it changed the room in which questions are asked. Atmospheres that had been abstractions became measurements. Clouds that had been excuses became parameters. Heat that had been a metaphor became a temperature profile. Molecules that had been rumors became lines that anyone could see if they knew where to look. The class of planets larger than Earth and smaller than Neptune ceased to be a category held at arm's length. It became a weather report written across the infrared, changing with longitude and altitude, mapped not with photographs, but with spectra that feel like cartography anyway. Time leaves marks even on light. A star that seems steady is in truth a metronome, its glow rising and falling by a fraction as spots turn across its face and as subtle pulsations ring through its body. Planets use these rhythms as clocks. With each orbit, a transit carves a shallow notch in brightness at a predictable minute. The minutes do not keep perfect order. Gravity tugs between neighbours, shift them forward or back by seconds, sometimes by minutes, writing a Morse code of delays across years of watching. From those delays, hidden masses step into view. A planet too small to be seen directly can reveal itself by the way it perturbs the schedule of a larger companion. The method asks for patience and pays with weight, eccentricity, and hints of inclination, all without a spectrograph touching the host spectrum. Transit timing variations behave like tides in the calendar. When two planets orbit near a simple ratio, their gravity exchanges momentum gently but insistently. The inner arrives a little early, then a little late, while the outer does the opposite. Their errors in antiphase, like dancers trading steps. The amplitude and period of this pattern encode the masses and the distance from exact resonance. A clean signal lets modelers disentangle both orbits and lift the veil of composition through density once a radius is known. Even noisy signals become eloquent when the record stretches long enough. The timing ledger turns data scarcity into strength by stacking orbits until the pattern cannot be denied. A sister to this technique listens for changes in duration. If a planet's path across the star shortens or lengthens slightly over years, the line of nodes may be precessing, or the eccentricity may be shifting under the pull of companions. Transit duration variations are quieter than timing drifts, but they reach for different physics. Nodal precession hints at mutual inclinations and at the quadrupole moment of the star. Apsidal precession points to tides within the planet and within the star, quantities that whisper about interior structure. When both timing and duration dance together, the system begins to confess not just who is present, but how stiff or pliant the bodies are, how mass is distributed beneath their photospheres and skies. Some orbits decay. The cause is the tide the planet raises on the star, and the tide the star raises on the planet. Energy lost as heat must be paid by orbital energy. The result is a slow spiral inward that appears in the timing record as transits arriving ever so slightly ahead of schedule. Detecting such a drift is the work of a decade, sometimes two, because the slope is shallow. A measured decay turns a vague parameter called the tidal quality factor into a number with units. That number in turn tells of stellar interiors and planetary rigidity. A handful of systems show hints of this fate, a soft surrender to friction that will, in deep time, end in a last flare when the planet crosses the point of no return. Starlight carries other clocks that date the hosts. Rotation periods emerge from spot modulation, dark freckles crossing the disk, and dimming the light by a hair on cycles of days or weeks. Young stars spin quickly and slow with age, as magnetized winds carry away angular momentum. Gyrochronology uses this spin down as a clock. The calibration is messy, dependent on mass and on magnetic temper, but it gives ages with a confidence that often surpasses broad isochron fits. Knowing the age of the lamp titans models of atmospheric escape, interior cooling, and orbital evolution. A planet bathing in a billion-year-old wind has endured a different childhood than a planet under a 10-billion-year-old Sunday. Another clock lives inside the star itself. Tiny oscillations ripple its photosphere like the surface of a drum. Astroseismology catches those ripples as flickers in brightness and decomposes them into modes that depend on density and sound speed inside the star. From these modes, mass and radius of the host are measured with remarkable precision, and ages follow from models that match the internal structure. Planets around such tuned stars inherit better radii and more honest timelines. When asteroseismic ages join the timing records of transits, the history of a system stops being mythology and becomes a chronicle with dates. Magnetic cycles write seasons in the spectra. The same dynamo that produces spots also waxes and wanes over years, altering the ultraviolet that sculpts planetary upper atmospheres. A long watch reveals these cycles and ties them to changes in apparent transit depth when unspotted and spotted chords are sampled by the planet on different visits. Correcting for this contamination is not just hygiene, it is a path to understanding the environment that governs escape and haze formation. The star does not merely backlight the planet. It ages the planet by brightening and dimming in the very colours that matter most for chemistry and loss. Star spot crossings during transits become rosary beads on the light curve. When a planet passes over a dark patch, the star briefly brightens relative to the transit baseline. These blips mark longitudes on the stellar surface and can be tracked from orbit to measure rotation and differential rotation. The pattern also reveals the relative alignment between the planet's orbital plane and the stellar spin. If a planet repeatedly hits the same active latitudes, the system is likely aligned. If spot encounters appear at inconsistent phases, a tilt may be present. Such alignment measurements, when joined with the timing evidence for past migration or present resonances, begin to sketch how the system was built and how it settled. Clusters provide a shortcut to time. Planets around stars in young associations and in open clusters inherit the group's age by membership. The clocks for these clusters come from well-understood stellar evolution, lithium depletion, and dynamics. Observing planets in such nurseries turns the sample into a snapshot across a timeline. Young worlds look puffy and their orbits crowded. Older analogues look compact and their families settled. Comparing the two catalogues pinches models of contraction and escape in ways a field sample cannot. The clusters act like tree rings stamped across the sky. Even the lack of timing variations can be a statement. A planet that orbits alone with relentless regularity challenges scenarios that predict crowded birth. If the transit times refuse to budge within seconds over many years, upper limits can be placed on unseen neighbours. Those limits press on models that invoke migration through chains of resonances, forcing a role for scattering, for disk winds that carve gaps, or for early photoevaporation that prunes the inner system before siblings can linger. The silence of a clock is not absence of information. It is a boundary around possible histories. Photons in high energy bands preserve the memory of youth. A star's ultraviolet and X-ray output decays with age, but the decay is not smooth. Flares and active phases pepper the record. Satellites that watch in these colors build cumulative doses for planetary atmospheres. Join those doses to timing-based ages, and the integrated assault on a planet's upper air can be computed rather than guessed. A planet that seems overstripped for its current irradiation may simply have endured a violent childhood. A planet that seems overdressed may have grown up under a gentle sun or contracted fast enough to lock its air away before the worst storms. Astrometry sends a final gift. Measuring the wobble of a star on the sky lays down orbits independent of transits and radial velocities. When a long astrometric record overlaps a long timing record, ambiguities collapse. The true masses of companions that cause timing drifts become clear without assuming they transit, and mutual inclinations can be inferred when the shapes do not align. The combined chronometers then resolve knots that each alone cannot. The result is a three-dimensional history told in calendars and in motions. The artistry of this approach is its insistence that time is not merely a parameter, but an instrument. Brightness drifts become scales. Delays and advances become signatures. Pulsations, rotations, cycles, and decay all merge into a choir that ages stars and weighs planets. When the ledgers of timing and duration, the clocks of rotation and pulsation, and the seasons of magnetism are read together, distance shrinks. The worlds do not grow nearer, yet their biographies gain chapters. They become old or young, hurried or patient, battered or sheltered, not by analogy but by measurement written in the only currency they can send across space, the rise and fall of starlight. Life considers pressure and light the way a composer considers silence. It listens, then chooses where to place its notes. Under thick hydrogen skies, the stage is unfamiliar, yet not hostile by default. The air is light in molecular weight and heavy in consequence. Scale heights swell, horizons soften, and a small amount of thermal energy keeps the lower layers warm long after distance from the star should have stilled the chemistry. If liquid water lies below, the lid turns into a greenhouse of uncommon efficiency. If an ocean is absent, a deep volatile mantle or a salty supercritical sea can still host gradients where energy moves from hot to cold, from reduced to oxidized, from dark to pale. Life does not require comfort. It requires disequilibrium and a route to harvest it. Hydrogen-rich air rewrites the menu of possible metabolisms. On Earth, energy often flows by shuttling electrons from donors like hydrogen or sulfide to acceptors like oxygen or nitrate. In a sky already saturated with hydrogen, the obvious donor is everywhere. The scarcity shifts to suitable acceptors. Carbon dioxide suspended in a hydrogen bath becomes a target. Reducing it to methane yields energy if catalysts and enzymes can find footholds at the pressures imposed by the overlying air. Nitrogen may accept electrons through pathways that build ammonia. Trace oxidants, if any persist from photochemistry high above, become precious currency. A biosphere that leans on such reactions will not exhale the same perfumes that mark life in oxygenated air. It will smell of reduced carbon and nitrogen compounds, of organosulfur whispers, of gases that on Earth can be made by cells or by vents, and must be judged by context instead of by presence alone. Pressure is not a wall. It is a tool that changes reaction rates and solubilities. At dozens to hundreds of bars, gases dissolve deeply into water and supercritical fluids. Hydrogen, that would escape quickly from a shallow pond can linger in a deep ocean, where microbes might harvest it near vent fields or fissures in high-pressure ices. Carbon dioxide that would form bubbles at 1 bar can disappear into solution and feed carbon fixation pathways without demanding sunlight at every step. Enzymes would need to tolerate compression. Membranes would need architectures that resist being squeezed into rigidity. On Earth, piezophiles have already solved such puzzles in trenches and lithospheres. The physics does not forbid similar solutions under alien skies. It encourages them. Light filters through hydrogen in unusual ways. Blue wavelengths scatter, reddening the day. Photons in the near-infrared pass more freely, warming deeper layers and giving photosystems a different palette to work with. If a haze grows in the upper air, the spectrum softens yet again, turning direct light into diffuse glow. Photosynthesis here could prefer pigments tuned to red and near-infrared, similar in spirit to those in bacteria that thrive beneath our oceans. The diffused field would favor broad mats or suspended colonies rather than tree-tall structures. The energy return per photon might be lower, but the total flux could suffice, especially on worlds orbiting small stars, where daylight lingers for long stretches and seasons are simple. Aerial niches appear naturally when the air thickens. Buoyant particles and droplets can levitate at levels where temperature is kind, pressure is manageable, and nutrients arrive from below as vapor or aerosol. Life that learns to ride convection cells and laminar updrafts could exist without ever touching a solid surface. Its shells would resist desiccation in hydrogen-dry air. Its metabolism would sip oxidants created by ultraviolet light far above, and reduced molecules rising from lower strata. Aggregates could form that shade each other and shepherd microclimates through a moving sky. Survival would depend on keeping to isobars the way plankton keep to thermoclines, not by muscle but by densities tuned to the wind. Nutrition cannot borrow the Earth's rivers. Trace metals and phosphorus would rise from the deep by vents and be carried upward by mixing rather than by watersheds. Lightning can fix nitrogen from the background and rain it out as nitrate or ammonium. Meteor dust can seed micronutrient cycles across global scales. The column becomes a vertical circulatory system. Upwellings feed, downwellings carry away waste, and long-lived eddies collect matter into temporary larders. Even without continents, cycles can run, slow but sufficient, their integrators measured in planetary radii instead of mountain ranges. Biosignatures must be chosen with more skepticism than romance. Oxygen and ozone will rarely accumulate under a hydrogen lid unless sustained by prodigious and improbable sources. Methane is not a prize by itself, because hydrogen atmospheres make it readily inorganically. Ammonia is fickle because ultraviolet light destroys it quickly, but that very fragility can turn it into a candidate under certain conditions. If it appears in abundance on a temperate world where photolysis should erase it, a living source becomes plausible. Nitrous oxide survives poorly in hydrogen without a protective filter from haze or clouds, yet it remains attractive as a sign of metabolism if ever detected alongside inconsistent companions. Phosphine, notorious in terrestrial debates, could become another such wild card, with abiotic paths tightly constrained and biotic paths hypothetical but feasible if the deep chemistry cooperates. Context is everything. Single molecules rarely convict. Combinations, ratios, and trends carry the weight. Disequilibrium is a more universal judge. A mixture of gases that should react away quickly, but does not imply continual renewal. On one template, excess methane with appreciable carbon dioxide and scarce carbon monoxide points to a source that manufactures reduced carbon faster than photochemistry can reoxidize it, while the star provides enough ultraviolet to keep carbon monoxide from saturating the air. On another, small yet persistent traces of oxidants coexisting with strong reducers require a conveyor belt of chemistry unlikely to run without biological help. Temporal variability adds leverage. Seasonal or quasi-seasonal oscillations in a gas whose lifetime is short suggest surface or cloud layer sources that breathe with the planet's cycles. Such rhythms can be distinguished from stellar activity by their phase and spectrum. Spectra speak more loudly in hydrogen air because the atmosphere is extended. Scale heights are large, so transmission signals deepen. This generosity cuts two ways. It helps detect faint molecules, and it makes stellar contamination and haze more intrusive. Retrievals must carry simultaneous allowances for clouds, star spots, and instrument slopes, or else false positives bloom. A disciplined approach would measure the same gas in multiple bands, check for pressure broadening that fits the expected altitude, and look for partner gases that tie the chemistry to a single, self-consistent temperature profile. If a candidate biosignature appears only in one corner of the spectrum and refuses to appear elsewhere, prudence demands silence rather than celebration. Surfaces may never be seen. That does not silence life. A biosphere that lives in the ocean or in cloud layers still leaves fingerprints by the way it alters the budgets of gases. It also leaves subtle marks on polarization. Light scattered by aerosols and droplets carries a polarization phase curve that depends on size, distributions, and refractive indices. Life that manufactures particular organic hazes could tweak those curves away from mineral expectations. Spectral edges from pigments might cast very gentle breaks in reflectance if clouds thin occasionally. None of these are decisive alone. Together, they build a circumstantial case that invites more time on target. Star type matters. Small stars flare and bathe planets in hard photons that can both seed interesting chemistry and erase signals. Hydrogen air can absorb and redistribute some of that energy. Thick lids shelter lower layers where life might operate. Bursts will still prune molecules with short lifetimes and push a biosphere toward products that are hardier or replaceable at speed. Around quieter stars, accumulation becomes easier, but motivation for haze may diminish, clearing windows that make spectra friendlier. The optimal theatre likely sits where ultraviolet is not relentless, where the orbit allows gentle days, and where the planet's gravity can hold onto its air long enough for slow metabolisms to build global inventories. False positives draw tight circles around enthusiasm. Deep abiotic chemistry in the mantle can vent reduced compounds. Water photolysis followed by hydrogen loss can leave oxygen behind in dry cases, counterfeiting a classic signature. Mineral catalysis on hot surfaces can write organics into the air without a ribosome in sight. The way forward is to reject simplicity. If a promising molecule is seen, test whether the planet's energy budget allows it to persist without a source. If it requires a source, test whether all known abiotic sources can meet the bill simultaneously with other measured gases. If they cannot, and if time variability supports a dynamic cycle that matches climate, the balance tips. The idea that life could breathe under swollen skies is not an exercise in optimism. It is a sober extension of chemistry. Hydrogen eases some constraints and tightens others. It extends the vertical laboratory where gradients can be mined. It softens the penalty for distance from a star. It complicates the hunt by muting familiar flags and amplifying strange ones. The reward for patience is direct. Worlds in this regime are abundant. Their air is generous to spectroscopy. Their climates are diverse enough to host niches. If biology has a taste for versatility, it will have tried this recipe. The most honest close is quiet. A spectrum awaits that shows a handful of gases reluctant to share a sky unless something below or within is replacing them. The ratios will resist equilibrium. The features will repeat across bands. The phase curves will shift with a rhythm that suggests seasons or overturning. No single line will glow with certainty. The whole will suggest metabolism humming behind the weather. If that day comes, the verdict will not be a shout. It will be a calm statement that under thick air and steady light, chemistry has quickened into something that harvests gradients and remembers to rebuild what time and starlight take away. Architects of planets work with powders and winds. In the first million years after a star lights, a disk of gas and solids rotates like a slow river around it. Dust grains touch, cling by van der Waals forces, and grow into pebbles. Pebbles drift inward because gas orbits slightly slower than Keplerian speed and robs them of momentum. Along that drift, tiny embryos wait. Each embryo eats pebbles as if holding out a net in a current. The feast does not last forever. When an embryo grows large enough, its gravity carves a pressure bump in the gas. Pebbles then stop drifting across that bump. The embryo has reached the pebble isolation mass, and the conveyor belt that fed it falls silent. This threshold explains more than it first appears to. It decides who becomes a giant and who stalls in the realm between Earth and Neptune. Simulations paint the process in frames. In one, the disk is rich in solids and calm. Pebbles arrive fast. The isolation mass is reached quickly, and a core of roughly 10 Earth masses forms before the gas thins. That core binds an envelope, cools it by radiation, and then accretes gas faster than pebbles can continue to arrive. Runaway begins. The planet crosses from intermediate to giant. In another frame, the disk is modest in solids or turbulent. Pebbles collide and fragment before growing. The core grows slowly and reaches isolation late, perhaps after the gas has already begun to disperse under ultraviolet light from the young star. The same embryo that could have seeded a giant instead becomes a super-Earth or a sub-Neptune, its envelope a thin veil that never catches fire into runaway. Pressure bumps sculpt the nursery like sandbars in a river. A bump can arise where the disk is heated by stellar radiation, often near the water ice line. It can arise where magnetic effects launch a disk wind that removes gas and steepens pressure gradients. It can arise where viscosity changes across the boundary of a dead zone. Embryos that park at these bumps collect pebbles efficiently. Those that miss the parking spots starve while neighbors grow fat. The result is a lumpy initial map where seeds of similar birth time end with different futures. In a disk with a strong inner bump, many embryos stall before they can drink deep from gas. In a disk with weaker structure, more cross the boundary into runaway. Metals in the star set the budget. A metal-rich star formed from a cloud that seeded its disk with more solids. In such disks, pebbles are abundant and isolation masses are reached quickly. The statistics show a correlation between stellar metallicity and the presence of giants. At lower metallicity, intermediate worlds dominate. The trend is not a law, but it is strong enough to guide models. It suggests that the missing giants around many stars are not erased by later violence. They were never born because the supermarket closed early or the carts were small. Cores reached 4 or 5 Earth masses, bound a light atmosphere, and then watched the gas disperse. The disk was generous enough to build a crowd of mid-sized planets and stingy enough to keep giants rare. Opacity in the envelope acts like a thermostat. A core that binds gas must cool that gas so more can fall in. If the envelope is rich in tiny grains or heavy molecules, it radiates poorly and stays warm and puffy. Accretion stalls. If the envelope is clear and clean, it radiates efficiently and contracts. Accretion accelerates and soon runs away. Simulations that vary the opacity watch the same core become a giant in one run and remain a sub-Neptune in another. The difference is not dramatic in appearance. It is a trace of dust and metals mixed into the newborn air. Pebble accretion itself can feed the envelope with grains. Whether those grains survive or evaporate on the way in becomes decisive. Disk winds thin the stage from above. Magnetically driven flows lift gas off the disk and carry it away. As gas surface density drops, pebbles decouple from the flow and drift inward faster. Embryos close to pressure maxima gorge. Embryos far from them experience a famine. The wind also sculpts cavities that trap solids and halt inward drift. Where the wind is strong, current lines in simulations open gaps early and drive a pattern of 2 or 3 favoured parking rings. Many seeds collect in these corrals, each competing for the same pebbles. None dominate strongly enough to trigger runaway accretion before the gas is gone. The final picture is a compact, multi-planet system of intermediate worlds. each separated by a few mutual hill radii, stable and quiet. Migration moves the pieces while the game is still being played. When a core grows, it excites spirals in the gas that pull on it. The torque is not symmetric. The imbalance drives the core inward on a timescale that depends on disk temperature and density. If the core migrates into a pressure trap, it stays and continues to accrete solids. If it misses the trap, it can dive toward the inner disk and park near the star. In both cases, the timing relative to gas dispersal decides whether the envelope grows thick. Rapid migration without efficient gas cooling tends to populate the inner system with super-Earths and sub-Neptunes. Slow migration, combined with clean envelopes, tends to allow one or two giants to emerge farther out. The architecture we see later is a freeze frame of where the pieces stood when the gas evaporated. The snow lines act like gates that open and close. Water condenses at one distance, carbon monoxide at another, carbon dioxide between them. Beyond each line, solids become more abundant, because a volatile that was vapor now becomes ice and sticks to pebbles. Cores that form just outside a snow line get an early advantage. They grow faster and might reach isolation while gas still lingers. If migration carries them inward, they bring ice-rich compositions into warmer zones. If the disk clears before they collect much gas, they appear later as intermediate planets with volatile mantles and thin hydrogen veils. If the disk remains, they turn toward gas capture and cross the threshold into giants. The location of these lines moves as the disk cools, adding another layer of timing to a story already rich with clocks. Collisions write footnotes that can be mistaken for plot. After gas dispersal, planetesimals and protoplanets no longer feel the softening presence of drag. Orbits cross, worlds collide. In one outcome, two sub-Neptunes smash together and lose a fraction of their envelopes while merging cores. The result is a single planet with higher density that still remembers a thin sky. In another outcome, an impact removes the envelope entirely, leaving a bare super-Earth next to a slightly puffier sibling that was spared. The events adjust radii and densities without changing the seeds that disk physics planted. To an observer, the system will still look short on giants. To a modeler, the collisions explain scatter within a category, not the category itself. Low-mass stars add a new pattern. Their disks are lighter in gas, their ice lines closer in, their pebbles fewer. The pebble isolation mass is smaller, often just a few Earth masses. Few cores around such stars break the barrier that triggers runaway. The result is a preponderance of intermediate planets packed close to their suns. When a giant appears, it is often a solitary sculpture amid dwarfs. This trend fits with the scarcity of giant planets around red dwarfs and the ubiquity of mid-sized planets in their habitable zones. Missing giants here are not a mystery. They are a natural consequence of lean nurseries. Gaps carved by planets feed back on growth. A core that raises a shallow depression in gas starves not only itself of pebbles once isolation is reached, it starves embryos interior to it by diverting their supply. A single early core can therefore suppress growth downstream, locking smaller neighbours into a forever intermediate scale. If several cores form at similar times, they reach isolation together, leaving the inner system full but ceilinged below runaway. The choreography is subtle. Who forms first by 100,000 years shifts the final skyline of a planetary system by thousands of kilometers in radius. Turbulence tunes the stickiness of pebbles and the thickness of the midplane where they concentrate. High turbulence stirs solids up, reducing the density in the thin layer where streaming instabilities would otherwise clump them into kilometer-sized bodies quickly. Low turbulence allows sharp midplane bands that spawn planetesimals. An intermediate level might produce pebbles efficiently but then shatter them in collisions before embryos can catch enough. Simulations that sweep turbulence across a plausible range see a spectrum of outcomes. Calm disks tend to build larger cores earlier and accept giants. Busy disks tend to saturate with sub-Neptunes and super-Earths. Even chemistry in the gas changes the map. If carbon to oxygen ratios in the disk differ from stellar values due to selective drift and freeze out, the opacity and cooling of envelopes shift, altering the chance of runaway. If sulfur or sodium-bearing species condense at particular radii, they introduce cloud layers in envelopes that modify how heat leaks out. Tiny changes in radiative efficiency alter the race between cooling and dispersal. The consequences are large only because the thresholds are close. The difference between almost giant and mid-size is not dramatic in mass. It is dramatic in how the envelope behaves. At the end, the phrase missing giants becomes a summary of timing, supply, and cooling. Cores that grew on time, in places where pebbles pooled, under skies that radiated well, became seeds that the disk could fatten into giants. Cores that grew late, in corridors with less drift, or under envelopes too opaque to cool, remained between Earth and Neptune. Disk winds hustled the gas away, pressure bumps built gates, metallicity set the pantry, migration shuffled chairs, and collisions rearranged details after the music stopped. The commonness of intermediate planets and the relative rarity of giants do not require an accident. They follow from a theatre where the closing curtain descends quickly, and where most actors only have time to reach the middle stage. Sometimes a map is drawn by what is not there. The neighbourhood around a familiar star holds 4 small stones and 2 giants that keep respectful distance. Between the 4th rock and the first ice giant there is no planet of intermediate scale. Inside the orbit of the innermost rock there is a silence where many other systems carry chains of close companions. The absences do not feel like a quirk. They look structural, as if an architect erased a whole category from the blueprint and left the erasure visible in the grain of the wood. Read carefully. The missing worlds turn into evidence that points back toward the nursery where this system learned its habits. Pebbles once drifted through the young disk like a wind of dust. Where nothing blocked them, they fed embryos and swelled cores. A single massive core can turn this drift into a dam. By carving a pressure bump in gas, it arrests the inward traffic of solids. A young giant near the snow line would have done exactly that. The flow from far regions would have stalled, starving the inner disk of the extra solids needed to push embryos across the threshold where envelopes grow deep. If a planet of Jupiter's scale raised that barrier early, the inner family would remain modest, never crossing into the swollen regime that fills other skies. Migration leaves fingerprints in orbital architecture. A giant that wandered inward and then outward could have pruned the inner disk to a narrow ring of rock. Such a journey would scatter planetesimals, stir the asteroid belt into a museum of contrasts, and reset the inventory of solids between 1/2 and 2 astronomical units. Embryos left in a trimmed corridor would collide, until 2 mid-size worlds formed, and a small neighbour survived as a relic. Mars would come out undersized. The belt would become a patchwork of carbon-rich bodies and drier cousins. All of these are the patterns seen today. The lack of intermediate planets near the star then becomes a consequence of early giant choreography rather than a missing step in nature's dance. Gas fades from a disk in only a few million years. If the clock ran quickly here, cores had little time to bind thick skies before the supply vanished. A brief gas era helps explain why no small world carries a light envelope today. It also keeps ice giants far and light, never allowed to gather enough to become second giants. The timeline matters. A system with longer gas would tend to fatten seeds into mid-sized planets near the star and into more massive giants beyond. A system with shorter gas ends with leaner outcomes at every radius. The solar calendar appears to have offered just enough time for a single giant to grow early and impose order, then close the window before inner embryos could drink deeply. The star itself spent youth as a restless lamp. High energy light from a newborn sun would have driven escape from any thin hydrogen veils that small worlds attempted to keep. The inner 4 bear the scars of such weathering. Mercury is bare and metal-rich. Venus carries a heavy air, but not the type that would point to a primordial envelope. Earth preserves only whispers of ancient hydrogen in trapped minerals and in noble gas ratios. Mars wears a light cloak that likely thinned long ago. The pattern implies that even if tiny envelopes formed, they did not survive. Without deep gas from the disk and with an active young star overhead, the path to intermediate size was closed from above, as well as from supply below. Meteorites carry isotopes like hallmarks from their origins. Two families appear, with a chemical divide that suggests a barrier in the disk. One family likely formed inside the orbit of a young giant. The other formed beyond it. The separation persisted long enough for their chemistry to diverge. This implies that a large body held position as a wall early in the story. Such a wall would have shaped where pebbles collected and where they were denied. It would also have acted as a guardian that kept the inner region dry enough to avoid growing thick, volatile mantles that swell radii. The Earth's modest water budget fits this reading. Enough delivery for oceans and plate motion, not enough for a global mantle of exotic ice. The inner system lacks the tight chains of close worlds found elsewhere. Inside the innermost orbit there is only the Sunday. Some maps of planet formation suggest that solids there were ground down into dust and swept into the star before embryos could form. Others suggest that migrating pebbles were filtered before reaching those radii. Either way, the silence speaks. It says that this system did not favor the compact architectures that make intermediate planets easy to find in transit surveys. The missing inner chain tells as much about the supply lines of the disk as the missing mid-range world tells about the timing of gas and the interference of a giant neighbor. Resonances offer another clue. Many intermediate planets elsewhere sit in gentle near-resonant sequences, a memory of migration through gas. The inner four here do not. Their periods bear no simple ratios. The absence of near commensurabilities hints that gas either cleared early or that a later event erased smooth patterns. Collisions after gas dispersal would do so, scrambling periods and eccentricities and halting the delicate shepherding that builds neatly spaced mid-sized families. The roughness of the pattern becomes a signature that points to late violence over long migration. Even the moons of the giants weigh in. One giant carries a regular assembly of icy satellites that could have formed in a circumplanetary disk rich in water. Another carries a more knotted collection. Their differences reflect how each giant accreted gas and solids, and how quickly their feeding zones emptied. If the outer region had been flush with solids for long, more giants might have formed, or existing giants might have grown heavier. The fact that two giants rule, and two ice giants trail, suggests a disk that thins steadily, and a decisive early barrier that quarantines supplies. This speaks against a nursery that would have fed many mid-sized worlds inside the frost. The absences matter not because humanity lives among them, but because they test whether the rules of formation travel well. They do. Place a giant early and watch the inner disk remain slim. Shorten the gas era and watch small worlds shed their breath. Allow collisions to follow and watch orbits lose any elegant spacing. Each step takes away the chance to halt in the intermediate regime. None require a special pleading for privilege. The path to a system like this is plausible in simulations that respect the physics of pebbles, gas, and time. There is a tempering lesson in the statistics. Many stars display intermediate planets in abundance. A significant fraction do not. The solar map sits within that second set. Typicality and uniqueness trade places, depending on what trait is measured. In overall architecture, with small inner worlds and giants beyond a gap, the map is not freakish. In the specific absence of mid-sized members, it sits left of center on a distribution that includes both haves and have-nots. The danger is to call one state normal and the other deviant. Better to treat both as outcomes of clocks and barriers that differ only slightly from star to star. This reframing has consequences for how habitability is imagined. A system without mid-sized worlds near the star offers wide, stable lanes for temperate orbits, fewer strong perturbers, and a history where water delivery came in measured parcels rather than in floods. A system with mid-sized neighbours close to the lamp may experience different delivery of volatiles, different tides, and different protection or exposure to impacts. Neither pattern guarantees gardens or deserts. Each sets boundary conditions under which climate and geology perform their long negotiation. The missing planets here become part of that negotiation by their silence. Absence sharpens the eye more than presence. It obliges theory to explain not only how to make something, but how to fail to make it. It turns the system into a benchmark against which other systems can be compared, not as a standard, but as a point on a map with coordinates labelled by barriers, clocks, and migrations. The erasures on this map are instructive. They show where a giant stood early and where a river of pebbles stopped. They show how fast the gas curtain fell. They show where collisions made the last edits. In that sense, the solar system is generous. It does not offer an intermediate world to study in the backyard, but it offers a clean absence that can be read with confidence. The final comfort is subtle. A world can be understood by what it is not allowed to be. A system can be understood by what it did not build. In the long catalogue of planetary families, this one writes its identity partly in negative space. That space is not emptiness. It is a record. The giants that kept watch early, the gas that fled on schedule, the pebbles that were halted at a distance, the collisions that wrote the last lines. Put together, they explain why the most common silhouette elsewhere does not rise here. The map is complete enough to navigate by, even where the paper is blank. Answers seldom arrive with trumpets. They step out of the noise like shoreline from fog, a little more of the line revealed with each incoming tide. The planets that sit between Earth and Neptune have taught this cadence well. Their shapes first appeared as dips in light. Their densities then unfolded as stars wobbled. Their skies started to speak when infrared prisms opened. Patterns emerged and refused to flatten into a single rule. A valley in size separated two crowds that seemed related yet lived under different fates. Explanations multiplied, each grounded in physics, each carrying promises to keep. The subject did not collapse into certainty. It matured toward patience. Patience has instruments. One listens for the same transit 100 times and watches the minute hand drift by seconds that feel like footsteps of gravity. One spreads a spectrum until a familiar water band rises above haze and says, softly, that clouds are present but not sovereign. One weighs a star with its own pulsations and rewrites a planet's radius to 3 significant figures instead of 2. One runs a climate model 10,000 times with slightly altered starting values until the jets and vortices settle into families that match the light curve. The craft looks like repetition. It is in truth refinement, because each repetition is not the same experiment, but the next rung of a ladder built from memory. The patience also lives in the choice of targets. Some worlds are bright and close, and their stars quiet, perfect for learning how retrievals fail and how they can be made honest. Others are temperate enough to tempt thoughts of oceans, yet still wrapped in gas, generous to spectroscopy, perfect for testing whether chemistry hints at deep water or deep air. A third group is extreme, hot and fast, where clouds flash in and out of existence, and escape is caught in the act. These act as boundary stones that tell theory where physics must bend and where it cannot. With each category, confidence rises that the lessons are portable. There is a humility to the pace. A single planet can consume a season of instrument time. A single improvement in pipeline can lift or erase a feature that entire arguments once leaned on. A single measurement of helium loss can chase away an assumption about survival and replace it with a rate that turns billions of years into a timetable written in millions. The instruments are strong, but the distances are stubborn, and the atmosphere at the top of each world is not obligated to be clear where human eyes most want to look. Progress is not a conquest. It is a correspondence, and the other party writes in faint ink. The long patience of answers includes the anticipation of tools still in their cradles. Mirrors larger than theatres will climb mountains and piece starlight into threads so fine that winds on distant planets might be traced by their Doppler tilt. Coronagraphs will carve darkness near bright stars and let reflected light whisper about clouds that shine like frost or oceans that drink the day. Small fleets may one day watch the same system together, one catching the optical sheen, another the infrared warmth, a third the radio hiss near a magnetic pole. Coordination will turn snapshots into albums, and albums into time-lapse. There is also patience in the laboratory, where matter is taught to remember planets. Water is crushed until it becomes a crystal that flows like rock. Hydrogen is pushed into states that mimic metallic seas. Photochemistry is coaxed through reactions that build haze under lamps chosen to match the spectra of small suns. The constants that go into models are not sacred numbers kept in old books. They are measurements wrestled from conditions that no casual experiment can reach. Each revision turns a guess into a table, and tables teach telescopes how to read what they see. The patience is ethical as well as technical. Worlds measured with such intimacy become mirrors for hopes that travel quickly and for claims that travel faster. A spectrum that looks like life to an eager eye looks like chemistry to a careful one, and the careful eye prevails by insisting on replication across bands and seasons and instruments. The discipline that refuses a headline until the pattern repeats is not timidity, it is fidelity to distance. It is respect for a subject that cannot answer back, if misunderstood. Time will thin the tangle of explanations. If light from 1,000 systems maps the depth and tilt of the radius valley as a joint function of stellar age and brightness, then the share of the sculpting done by starlight from above will sort from the share done by heat from within. If metallicity and water lines and carbon dioxide bands combine to place strong limits on envelope fractions, then the share done by disk timing will settle into clear percentages. If helium tails are caught often and at many levels of irradiation, escape will become a measured budget item, not a line of poetry. If phase curves gather into families that match model families, circulation will stop being folklore and become climate. Even as the answers firm, surprises will persist. A planet slightly larger than Earth will weigh too little and force the inference of a mantle of ice that defies the stereotype of small and rocky. A world classified by size as a cousin of Neptune will betray an envelope so thin that it cannot be kin to a giant, only to a stone wrapped in a veil. A system will present near twins by radius that show opposite climates, one hazy and flat, the other crystal clear and chatty. Those contrasts will not unsettle the map. They will sharpen it, because a strong rule allows the exception to teach precisely where the border lies. Patience is not a synonym for delay. It is a mode of attention that keeps faith with the scale of the subject. Stars age slowly, planets cool slowly, atmospheres escape slowly when they are not being torn. The instruments that read these stories must be tuned to the same tempos. A decade of timing becomes a paragraph in a history that spans billions of orbits. A year of spectra becomes a long glance at weather that breathes in cycles longer than human endurance but shorter than geological time. With every orbit added to the ledger, with every wavelength stitched to its neighbour, the sketch deepens. The long patience finally becomes a promise. The worlds in question are common. Their air is cooperative. Their stars are accessible. No act of luck is needed to understand them, only skill and repetition. Only the kind of discipline that built observatories out of metals born in older stars, that laid detectors on tables steadied to microns, that wrote codes which turn ripples in light into temperatures and winds. The mystery is not infinite, it is intricate. The patience is not endless, it is exacting. Answers will arrive, not as sudden decrees, but as a coastline traced to finer and finer scale until even the inlets are named. When the maps are finally detailed, the category will not vanish. It will become a landscape with neighbourhoods. Some districts will be carved by light, their citizens lean and rocky, their skies rebuilt by outgassing. Others will be softened by inherited air, their seas deep, their clouds stubborn, their climates steady under a lantern of hydrogen. Between them will run the old riverbed in the histogram, no longer mysterious, now a memorial to thresholds that planets cross or fail to cross, while the gas in their nurseries lasts. The patients will have paid not with a single noun for what these worlds are, but with a grammar for how they become. The reward will not be an end of questions. It will be a change of questions. From what are they, to how many climates can they host? From where did they form, to how often do they carry oceans? From can life breathe here, to what signatures of life are most likely in air that is light, in seas that are deep, under stars that are red? The shift will be natural, because patience is not only the willingness to wait, it is the ability to change focus when waiting has done its work. Night returns to its slow work, and the telescopes keep their quiet vows. Somewhere a planet crosses a small sun, and the light dims by less than a whisper. Somewhere a thin river of hydrogen lifts into space and makes a veil that glows for a moment, then is gone. Somewhere a cloud of salts rises, bright as frost, and turns a spectrum into a soft blur that only persistence can untangle. The sky does not hurry. It leans into long time and invites those who study it to learn the same habit. In the rooms where data gathers, screens glow like low constellations. Curves are folded and refolded. Dots are weighed and labelled. A line grows sure where it was once hesitant. A feature repeats where it once hid. The work looks ordinary from the hallway. It is not. It is a way of listening so carefully that the world beyond the world speaks back. The planets that learn to live between stone and giant do not need names to do their work. They need only orbits and light and the long patience of attention. Out of that attention will come climates, then weather, then maps drawn without photographs, only with spectra that carry the taste of air. Out of that attention will come stories of birth told by pebbles and winds, of seas that never meet a shore, of heat that bleeds like memory. When morning returns to the domes and the mirrors rest, the questions remain, untroubled and undiminished. They are not a burden. They are the music that keeps the instruments tuned. A century from now, the same family of worlds will still cross the same stars. The notes will be clearer. The patience will have done its work. Somewhere, an ocean will move under a pale lamp in air that is light, and a chemistry will decide to become more than weather.